wire connector, which looks very similar to this RJ45 connector, which we see on Ethernet cables or twisted pair cables. You can see in the image on the right, I have this twisted pair cable with an RJ45 connector on it plugged into a jack. You can see that little clip on the top there. If we push that down, we're able to pull that jack out of the interface. These are set up very specifically. So these connectors are configured very specifically. And one of your jobs might be, as a network technician, might be to replace these cable ends. So when we're looking at how these cable ends are spec'd out, the pins are numbered. So if the clip is behind you and you have it positioned exactly as I have it shown in this picture, pin 1 is at the top, pin 8 is at the bottom. We typically only use 4 of the wires to actually transmit data. The other 4 wires are still needed, but they actually don't pass data networking traffic typically. We just need them connected to make the cable work correctly. So pins 1 and 2 are the transmit wires. Pins 3 and 6 are the receive wires. The other pins, 4 and 5 and 7 and 8, those are not used, but they do need to be connected. Now, if you notice in this connector, you can kind of see through the connector, you'll notice that the pair of wires that's white, orange, and orange are connected to pins 1 and 2. And you can't really make out the color of pin 3's wire, but if you look down at pin 6, you can see that it's green, and that means that pin 3 is going to be white-green. So it's very, very important that we get the pairs of the wires correctly on here in order to make this cable work as efficiently as possible. If you don't get this right and you don't get the order of these wires correctly connected to the right pins, you can reduce the capacity of the cable by 70, 80% or more even. So we really want to make sure that these pins are configured correctly in order to get our cables to work right. And the specification we use in order to do that is one from EIA-TIA, and it's 568B. So we're going to look at 568A as well in just a moment here, but the ones that we use for most cables when we're putting the ends on a cable is 568B. And what that means is pin 1 is white-orange, pin 2 is orange, pin 3 is white-green, pin 4 is blue, pin 5 is white-blue, pin 6 is green, 7 is white-brown, and 8 is brown. We want to make sure we get these wires, these pairs of wires, in the exact right pin number in our jack to meet our specification. So the category 5, 6, 7 cabling color here, we have the 4 different colors with its white paired color, so orange, white, orange, and so on. When we hook them up to our straight through cable using 568B, we can see that we have white, orange, orange, and then pin 3 is white, green, and pin 6 is green. This is a straight through cable. This is used for most applications. And we can also make something called a crossover cable. And the crossover cable here, what it will do is it will take the transmit wire of one end of the cable and it will connect it to the receive end of the other end of the cable. So, and when we do this, we put 568B specification on one side and 568A specification on the other side. Now, you might be saying, Ross, like you just told us a messy story here about a straight through and a crossover cable and how they're built, but we don't know how they're used. So yeah, I understand that. So these cable types, straight through and crossover cables, you need to know the difference between these two and where they're used and which specification goes at each end of the cable for each one. So a straight through cable is going to be 568B on both sides. Crossover cable will have 568A at one side and 568B on the other side. We can tell the difference between a crossover cable and a straight through cable by comparing the RJ45's ends side by side. In our straight through cable, it should be white, orange, and orange on pins 1 and 2, which are the leftmost pins in this picture. In our crossover cable, we should have white, green, and green on one side and white, orange, and orange on the other side. Now, when we use these cables, we want to use a crossover cable when we're going from like device to like device, so router to router. We haven't talked a lot about routers yet, but the circle with the arrows in it, those are routers. We have switch to switch. This image here is with the lines going horizontally or the arrows going horizontally. That is a switch image or a switch icon. Or a PC here, if we have PC to PC, we're going to use a crossover cable. Let's mix this up and do a couple other examples here. When we're going from a PC to a router, this is one weird case where we use a crossover cable. Routers are kind of like a PC. It's kind of like a server that does routing of data network traffic. So it's kind of like a like device to a PC. But when we go from a PC to a switch, that is a straight through cable. When we go from a switch to a router, that's a straight through cable. And the real truth of the matter here is that almost all modern devices use a technology called automitics, which is auto medium dependent interface crossover. I don't expect anybody to remember all what that word means, but if you hear somebody say, oh, automitics is on there, you don't need to worry about the cable, what that means is that you can use any cable, a crossover or a straight through cable, to connect two devices together, and the network interface cards, or NICs, on those devices will automatically figure out if it needs to be a crossover or a straight through, and it'll electronically reassign the pins for us. Another one we need to talk about here now is coax cabling. Now, the coax cabling that you're likely most familiar with is the one that comes into your house that either provides you cable TV, if you still have that, or cable internet. This is going to use an RG-6 cable. It's the one I have shown over on the left-hand side of the slide. And that RG-6 cable is going to use an F-type connector. So that F-type connector is a screw-on connector with the wire sticking out the middle. That wire sticking out the middle is what we use for carrying the signal. There's some shielding on that cable as well. And we can use that to provide cable internet and cable TV. Another type of coax cabling that you'll likely see in a data center that can transmit data at 10 gigabits or 40 gigabits even is something called a twin axial cable, or twinax. And twinax, you'll often see it'll come with the network interface cards built right into the cable. That's what we're looking at there. Those are called SFPs. We'll learn a little bit more about SFPs in the next coming slides when we talk about fiber optics. But here with a twinax cable, we might use this in a data center to connect switches or routers or servers or storage area networks together. These can be a little bit less expensive than using a fiber optic system. If you're working with very old school technology, especially old school telephone systems, so most of you that are watching this may never encounter this at all, but if you do work in an environment where they're using very old school telephone systems yet, and they're not on voice over IP, you might encounter something called a 66 block. And a 66 block is a bunch of connectors here where we can push one of our twisted pair wires into it and it connects them together. In this block here, each row of pins or jacks there that you see the wires going into, each row is all connected together, so it's all one circuit. So when we do this, we can actually hook together phone systems doing this and create extensions and whatnot. You won't see this in data networking at all. Another version of this is something called a 110 block, and that's just a bigger version of the 66 block, and it accomplishes generally the same exact thing. Something that you will likely encounter in the field if you are working on cabling is something called a punch down tool, and this is a punch down tool. The end on the punch down tool here is the important part. The punch down tool is a little bit spring loaded, so as you push it, when you get to the end and you're pushing the wire into one of those blocks or some type of patch panel, the spring will pop and it's going to actually cut off the wire. So you should notice on the image here in that purple circle, there is a little wedge at the end of that punch down tool. So this tool is going to allow you to push a wire into one of those punch down blocks, and then it'll cut off the excess wire as you do it to make a nice clean install. We'll see an image of this in a little bit. Now those ends on this punch down tool can come in one of several different types. One is called Crone, one is called 110, and another one is called Bix. And those are for just different systems of pushing wires into some type of patch panel. So here is a patch panel. It is not connected to a rack at this point, But the patch panel is a place where you would run the cables from some central location where like a switch is to each individual desktop or each individual server in an office building or in a data center. If you look at the back side of that patch panel, what you'll see is a bunch of punch down locations. So here you can see there's like some white strips with colors coded on them, and those colors represent each of the pairs of the twisted pair cabling. So what we would do is you'd cut open the cable, cut open that twisted pair cable, and then run each wire to the correct spot in that punch down panel or in that patch panel, and then you'd use your punch down tool to push that wire in there securely and cut off the excess. So that's how we use the punch down tool to push these wires into those jacks, and then we can connect a patch cable at the other end from the jack onto a switch or to a PC. That wraps up our talk about copper cables. Let's talk now about fiber optics. Now, fiber optics are really nifty stuff. They're really, really cool. What we do is we take a very, very, very thin piece of glass. It can be as thin as your hair or thinner. And we wrap it in lots of insulation and armor to protect it. So the fiber optic cabling itself can be relatively thick compared to the actual fiber that's going through it. And the whole reason we make it thick is to prevent that cable from getting damaged. Now there's two types of fiber optic cabling that we can use here, and the different types have to do with the thickness and quality of the glass used in the fiber. So the top one here, single mode fiber, that fiber optic is very, very, very thin, has very, very tight specifications for the quality of glass used. And when we send laser light through it, it takes a very straight path through the glass. There's very little attenuation or loss of signal as the laser passes through the fiber optic, which means that single mode fiber can go very long distances. Multi-mode fiber is a slightly lower quality glass and is a slightly thicker fiber optic, which makes it cheaper to make, which means that we can use it in applications where we don't need to go 10 kilometers. Maybe we only need to go 1 kilometer. And we can use multi-mode fiber then, which is a more economical way to do this. When we pass laser light into the multi-mode fiber, it has a tendency to bounce around the sides of the fiber optic a lot more, which can attenuate the signal or reduce the strength of the signal as it moves farther and farther down the cable. So single mode fiber we use for long distances, multi-mode fiber we use for shorter distances when we can because it's less expensive. Single mode fiber characteristically has a yellow jacket around it. Multi-mode characteristically has an orange jacket around it. Sometimes multi-mode fiber, as we'll see later on, will have an aqua jacket around it as well. Depends upon the speed of Ethernet we're using with it. Now, where do we use single mode versus multi-mode? So if we have two office buildings here and we need to run some data networking in here, we may have a switch on the first floor of each of these buildings and we need to connect it to a switch on the top floor. Well, if we're using copper cables, there's a limitation. We can only go 100 meters. If it's more than 100 meters, we are unable to use copper anymore unless we put in a repeater, which is messy, or otherwise we're going to have to use fiber optics. And typically we would use multi-mode as our next option. So multi-mode fiber, what we could do is we could connect the switch on the bottom of the office building to the switch on the top of the office building using multi-mode fiber. If we want to connect these two buildings together, we can use single mode fiber. Assuming these buildings are a couple miles apart or 10 kilometers apart, we can use single mode fiber to connect these two buildings together. So oftentimes we're using multi-mode fiber within a building or maybe on a campus where buildings are very near each other. And then we'll use single mode fiber when the buildings are far apart and we need to transfer the signal for long distances. Some specifications on single mode versus multi-mode fiber optics here. The laser type that we typically talk about when we're using single mode is LX or LR. When we're talking about multi-mode, it's SX or SR, and the way I remember those in my mind is the L stands for long haul, the S stands for short haul. So if we need a long distance, we're going to use single mode fiber, that's LX. If we need the shorter distances, that's single mode fiber, and that's SX. The wavelengths of light here involved with the lasers, the most important part here is that knowing just that there's different wavelengths of lasers that we're going to use here, and these wavelengths of lasers we use here are not actually visible to the human eye. However, they can damage the human eye. We're going to take a little bit deeper look at that in just a second here. Some of the optical network interface cards that we use, these optical network interface cards, sometimes they're called optics, sometimes they're called lasers, sometimes they're called a NIC. Just know that when we're talking about fiber optics, we're going to use lasers to light up the fiber and transfer the data. Here are two different types of laser modules we can use. One is super old school, it's a GBIC. You can even see on that GBIC, it says multi-mode 850 nanometers, November 2003. So that's a pretty old device there. You're not going to see many of those GBICs used anymore. You're much more likely going to see a small form pluggable or SFP. The next generation of those are called SFP Plus with a little plus sign next to them. They look exactly the same as what you see here in this picture, and they plug into a special interface on a switch or a server or other network device. As technology moves forward, we're going to see faster and faster and faster communications. Here is some for QSFP and QSFP Plus. Now you should be able to recognize the SFP, the small form pluggable there, but the difference here is these are quad. So Q is for quad or 4. So these actually are 4 times the speed of a regular small form pluggable. Those all come in different speeds and have different characteristics. This is likely a 40 gig connection here, and it's using multi-mode fiber. If you remember earlier, I said sometimes the multi-mode fiber has an aqua colored jacket or this blue-green colored jacket, and that indicates that it's using a high-speed network interface card or high-speed lasers, in this case the QSFP or QSFP pluses. Here's an image of a GBIC in a very old device. This is a Catalyst 3500 switch. These are not made anymore, so you may see some legacy gear in your network. Maybe there's a system that just can't be touched and it's been running for decades. And you might see something like this where there might be a multi-mode laser or a single mode laser in there in the form of a GBIC, but it's likely going to be uncommon in modern networks. The connectors we have here, we have the ST connector. That's going to be a round type bayonet connector. We have an SC connector, and that is going to be a square type connector where each fiber in the pair gets its own large connector that we plug into. We have LC connectors. These are very common in modern networks. It's a small connector that plugs into an SFP. And then the bottom two, the MTRJ and the FC connectors, you are likely not going to see those in the real world unless you're looking at a very old or very specialized application. Now these connectors plug into patch panels. So here's a patch panel. Our patch panel is likely going to be in our data centers or in some central location. If it's a large office building, maybe all of the fiber optics are going to come into one central room, and then we can connect all those to switches. The reason we do this is we don't want to plug the fiber optic that's running through the walls right into our switch. We tend to plug and unplug at the switch more often than anywhere else. So what we do is we terminate the fiber on these patch panels, and then we use a shorter piece of fiber to plug into the patch panel so that we can plug it into our SFP or GBIC into our gear. Now when we're plugging these in, the connection that's made is they have to actually butt those little individual hairs of fiber optic glass right up against each other very precisely. So these connectors, its intention is to align that very, very precisely. And then we use a special type of contact there. So the ends of the fiber optics are polished sometimes at this angle. It's called an angled physical contact. So that when the connector pushes together, it pushes that fiber optic together so that it has that angle that connects it together, and this makes it very easy for the light to flow through that without losing much light. Anytime we have a connection or a break in the glass and we have to fix it or patch it or make some type of joint on it, we're going to lose some of the power of the signal through that joint. So when we have something like angled physical contact, that helps improve that connection to make that low loss. Another type we have here is ultra physical contact. And the way we do this is we put a chamfer on the ends of the fiber. Now, this is really minuscule sized, right? So this is very specialized equipment that's making these connections. And then when we butt the fiber together and we pass a light through it, we have a nice clean connection where we have very low loss of light with this ultra physical contact connection. Whenever we're looking at fiber optic operation, we're almost always using two fibers to achieve the connection. One is for transmitting information from one device to the other, and the other is for the other direction. In this type of communication, this is called simplex or simplex pair. And here, like one end of the connection on that top fiber, the laser is on the switch on the left, and then there's an eye for receiving that laser on the switch on the right on the top fiber. And then on the bottom fiber, it's flip-flopped, where the switch on the right has the laser and the switch on the left has the eye for watching that signal come in. Now, in specialized applications, especially in internet service providers that are providing fiber optic to the house, we would use bidirectional communication here, which means that the lasers, the optics that we put at each end of this are going to be able to send light into the fiber as well as watch light that's coming through the fiber. Now, because we're using one fiber, what needs to happen is we need two different wavelengths of light in order to accomplish that. In order to do that, we use something called WDM, or wave division multiplexing. And we can actually use this wave division multiplexing in multiple operations. So a single piece of fiber like this, I actually looked at the fiber into my own home for my fiber optic internet connection, and there's only one fiber coming into my house. It's just a single fiber optic strand that's connected to a laser that can both send and receive data. And they do this because it's a lot more cost saving for an organization like an internet service provider, where they have fewer network interface cards to buy and they can have less equipment in order to support this, especially when there's lots of customers on a single area. Now, just like designations for Ethernet, when we talked about using twisted pair, we have the same thing happening in fiber optics. So here we're using either multi-mode or single mode fiber. The top one, 100 base FX, you're probably not going to see that much anymore, but that's going to use multi-mode fiber. That's 100 megabits per second using multi-mode fiber. 100 base SX, remember SX short haul, that's using multi-mode fiber. You may not see that either, but you will likely see somewhere in your career 1000 based SX. That's going to be a gigabit Ethernet connection using multi-mode fiber. And then we have gigabit LX using single mode fiber, long haul. We also have 10G based SR. The SR here is going to be 10 gigabit. It's going to be multi-mode fiber, and it's likely going to be the aqua colored fiber versus the orange colored fiber that we would use in the other types here. And then 10G based LR. LR here, again, long haul. That's going to be using single mode fiber in the yellow jacket. This is going to be all 10 gig. Talk a little bit about multiplexing before we wrap up this module. So multiplexing is a way where we can take multiple wavelengths of light and put them on the same fiber optic cable. So the way this works is, here's the electromagnetic spectrum. So the electromagnetic spectrum includes radio waves like AM, FM radio and TV, radar, the infrared from your TV remote control, or heat lamps when you go to a restaurant and they have food sitting under heat lamps. It includes the visible light spectrum, which is a rainbow, the Roy G. Biv rainbow. We have ultraviolet light that gives us a suntan. We have X-rays, right, that we use to peer into our bodies. And then as we go on from there, we have gamma rays and other types of rays. These types of waves in the electromagnetic spectrum are actually dangerous to humans because the wavelength on there is very tiny smaller than the size of an atom, and it can actually knock parts of the atom off and cause severe issues, especially for living creatures. So the idea here is that the electromagnetic spectrum is a bunch of waves, electromagnetic waves that have different wavelengths. On the left-hand side, those are very large wavelengths, 100 meters or more. At the visible light spectrum, we're in the nanometer area, and then over towards gamma rays, they're very, very, very tiny, the tiniest size being smaller than an atom. When we look at what we're using for fiber optics, we're using part of the spectrum that's right here on this orange line, all right? And that's part of the infrared spectrum. And we can't see it with our human eyes, but it will burn our retinas if we shine it into our eyes. Here's some of the wavelengths we can use. The idea here is that we're going to use multiple wavelengths and combine them together on a single fiber optic cable. Well, to do that, we're going to use prisms. So you may have seen a prism used to create some rainbows. You shine a white light through the prism and it creates a rainbow. And that rainbow is nothing more than the light separated out into its individual wavelengths. What we can do is if we shine a light into the prism, it's going to create a rainbow for us. It's going to separate those colors out, even the stuff that we can't see with our own human eyes. If we shine some rainbow light into a prism, we can have it output a single stream of white light. So the idea here now is that if we have 3 different lasers and we shine them into a prism, that prism can combine all 3 wavelengths into one single light that we can send through our fiber optic cable. And then at the other end of the cable, we can send that through a prism again, and it'll separate out that light into its individual colors again. This is really, really nifty technology, and it allows for us to have very high speed fiber optic connections of 100 gigabits or more. These are extremely fast connections that can go very long distances, and I guarantee you there are many parts of the internet that you use, likely even to watch this video now, that are making use of this technology of multiplexing. And those can go from 1 kilometer up to 70 kilometers, and even more if we have the right kind of gear. So there's 2 different types of multiplexing we can use. One is called coarse wave division multiplexing, or CWDM, and this is passive. There is no power to this. It's just little pieces of glass that combine the light into one stream and separate it back out into multiple streams. We can also do dense wave division multiplexing. And dense wave division multiplexing, or DWDM, that is going to be a powered system. We can fit a lot more wavelengths of light on this, so we can get a higher bandwidth. It can also go longer distances. So with the powered version, we have a lot more options to send a lot more data over the same link than we do with coarse wave. However, you're going to see coarse wave used in as many applications as possible because it is not powered, and that makes it very easy to use in many different situations. To wrap up this physical layer technologies conversation, we have talked about a lot of detailed stuff here. What we did was we started with the OSI model review and made sure we were looking at just the physical layer. We talked about the different mediums we can use, including copper, fiber optics, and electromagnetic spectrum with wireless. We talked about copper cabling, we talked about fiber optics and all the details of each of those, as well as the Ethernet designations for copper using twisted pair and for fiber optics using Ethernet up at layer 2. I hope this module was very valuable to you. We're going to move on next and talk about Ethernet at layer 2 so we can continue this progression about talking about enterprise network infrastructure. Welcome back. I'm Ross Bagurtis. This next module, we're going to focus on Ethernet terms and concepts. And I really wanted to combine everything about Ethernet into one module. However, there is a tremendous amount of information to talk about Ethernet. So the next two modules of this course are going to focus on Ethernet. We're going to start with terms and concepts here. Our goals for this module are first going to be to look at what CSMACD is, which is a very historic perspective of how Ethernet operates. We'll then talk about collision domains. We're going to talk about duplex and speed of Ethernet. And then we'll talk about the Ethernet frame. These are all very important concepts about Ethernet. So let's get started. Now, in the previous module of this course, we talked about the physical layer and most specifically the types of cables, both copper and fiber optics, that we need for Ethernet to work. Now we're going to talk about the data link layer protocol, Ethernet itself. Now the data link layer is responsible for moving data from one device to another device successfully. Sometimes we go to routers, and the routers are going to take
Did
that
they
message
pass
out
down
of
the
layer 2
information about
information and
the
put it in new layer
contractor
2
part?
information.
Yeah.
Most of the internet and business networks and home networks all make use extensively of Ethernet of some kind. So you likely have seen Ethernet in your home with some device similar to this. This is a cable modem router with a built-in wireless access point and layer 2 switch all built into one device.
There's nothing
This
wrong
is
with
an
the
Ethernet
cords.
device. If you look at the back of it,
The
you'll
card
see
reader's
that
taking it
next
and it's
along the
according to the
cable
CQ, it's
similar
letting
to
him
some
in.
cables here, you can
But the
actually
door,
see the EIA, TIA
sometimes when
568
people
port
go out,
specification in
it
that
doesn't
cable that's shown laying on
close
the table.
correctly in contact
This
with
is the switch on the
the
back of the
mechanism.
wireless router.
So it
This
gets
switch
locked.
here,
Yeah,
this is a Catalyst switch from
so
Cisco.
it
You
doesn't
might see
open.
this in an enterprise business.
That
This
sucks.
is a
Should we
48
report that?
port switch, much
Yeah,
larger than you'd have
no
in your
recording.
home. It even has 4 SFP slots over on the right. What we can do is plug in an SFP or a laser there to give fiber optic communication to this switch. Those are for small form pluggables where we could plug in some optics for fiber optic communication to this switch. Here's a data center or a network closet someplace where here we're using an HP switch to connect together a bunch of devices. Here you can see how we have the patch panel set up and we're connecting our devices from our patch panel down to that layer 2 switch at the bottom of the rack. So these are instances where you're going to see Ethernet. It's going to be very much the same as your home connection. However, it's just going to be bigger when we use it in businesses. Let's start with CSMACD. This is Carrier Sense Multiple Access with Collision Detection. Now, legitimately, we don't really talk about or use this today when we work with Ethernet. And the reason is that this is archaic technology. This is the original Ethernet that was originally made for industry back in 1982. Now, Ethernet itself has origins that date very far back, probably farther back than almost any other technology that we still use today. Ethernet was developed in the late 60s, early 70s by a guy named Robert Metcalf, who did this as a project for graduate studies, right? So it was his final project for his doctorate when he was studying engineering, and he made Ethernet, or something like Ethernet is today. Then in 82, several engineers got together and they wrote the official specification for Ethernet, which was then published by IEEE as a specification that you can purchase for relatively inexpensively. CSMACD, though, let's get back to that. The original Ethernet, the way it worked was we had a coax cable, a very thick, solid core coax cable, and our networked devices would attach to this cable, and they would all share the same exact cable. And in order for this to work, what would have to happen is each device on this cable would have to listen to the cable, make sure no one else was talking, and then when no one else was talking, then it would send data onto that wire. And the data that it sent onto the wire was in the form of some voltage, specifically plus 5 volts. So we would send this 5-volt signal out onto the wire, and then every device on this network segment would receive that signal. So the idea here with carrier sense multiple access is that multiple devices are using the same cable, and in order to pass messages on that cable, each device would listen for a break in the communication to find out when they could put signal onto the wire. When they were done transmitting, they would stop sending traffic, and then another device would keep listening to the wire for that break and then send traffic onto the wire to pass its information. Now, if for whatever reason, two devices happen to simultaneously listen to the wire, hear that no one's talking, and then start sending data onto the wire, well, then both devices would be sending 5 volts onto that wire. That would create a 10-volt spike of voltage, and that is a collision. So each device then would detect that a collision occurred. The device is sending traffic onto the network, would wait a random period of time, then listen to the wire again, see if anybody was talking, and then retransmit that data. So plus 10 volts is a voltage spike here, and the voltage spike is literally a collision. So carrier sense multiple access, we have lots of devices listening to one wire, waiting for an opportunity to talk. If two devices happen to accidentally talk at the same time, that's okay, that was intended. We have mechanisms then to detect that voltage spike or collision and then retransmit the data as necessary. So this creates something called a collision domain, and it's a group of network devices that will simultaneously detect a voltage spike. Now in modern networks, we don't actually use this. In modern networks, we use something different, and I'll show you why. So does CSMA-CD still exist? Yes. Are our devices listening to the wire, waiting for an open opportunity to talk? Yes. Do we ever have collisions in modern networks? Typically no, unless there's something broken. Which brings us to duplex and speed. This will answer the question for us in a little bit of why CSMA-CD doesn't describe Ethernet the way it once did. So duplex and speed in Ethernet, we have two options here. The first one in the original Ethernet specification all operated at half duplex. And my graphic on the left here describes this perfectly. I can send information from the top PC to the bottom PC, or I can send information from the bottom PC to the top PC, but never at the same time. So one device communicates at a time. This is a lot like a walkie-talkie, right? If I'm using a walkie-talkie, I push the button on the walkie-talkie, and when I'm pushing the button, I can't hear anything coming in, and I can talk then into the walkie-talkie, and anybody listening on that channel can hear me. They just can't talk back to me until I'm done. Once I'm done, I release the button on the walkie-talkie, and somebody else can then press the button and communicate back to me. But we can only do that one at a time. This is in contrast to full duplex communication, where both devices can send messages to each other simultaneously. So they communicate at the same exact time without worrying about collisions, and this is much more like the telephone. If I'm talking to my friend on the telephone, I can talk to my friend at the same time he or she is talking back to
Hello,
me.
this is Takeda
And we can
Security.
talk over each other this way. You may be
Takeda
enjoying this
Pharmaceutical
conversation
at
with each
Los
other, but
Angeles.
in a telephone conversation, sometimes we can send a message while the other person
Yes,
is
I
trying
would like
to
to report
acknowledge or
the
heard what they're saying.
B5
So if
main
I say
lobby
something
doors
around,
is
oh yeah, oh that's exciting,
not working
the other
properly.
person doesn't have to stop talking to me.
That's
We're just sending acknowledgement messages saying, yeah,
go
I
ahead.
heard you, keep going. So full duplex communication in Ethernet
Building
means that
5.
both devices can communicate at the same time. So when we look
Yes.
at this in a modern sense, when we connect our device to a switch, we're going to learn about how switches operate in the next module, but when we communicate with a switch, we can either send traffic from the switch to the device, this is half duplex, or we can send traffic from the device to the switch.
Yes, the main
And in
entrance
this
for
case, the
building
only
5.
time we're going to have a collision is if the switch and the
So the
PC
issue
send
is the card
information at the
reader.
same time. So
It's
this is a
taking the
little bit
badge
where the
swipe,
cable is
but it's not
slow
opening the
in half
door.
duplex communication, and maybe the PC
So
listens
according
to the
to our
wire,
system,
sees that the person talking, starts sending
it's
data.
letting the people
The switch
in,
does the
the
same thing. It
badge
sees that two
reader's
girls are
working,
talking
but
at the
the
same
door,
time, and there's a collision, a voltage spike. So this can happen if we're using haptic
somebody
communication.
comes out, the
But
door doesn't close properly, and the contact
we
points
have
doesn't
two channels open here. We can
meet,
send and receive data
and that's the
simultaneously.
reason why
And this
the
ability
door
means
doesn't
that
open.
we're going to have a collision because we have two channels to communicate on here. One to send to the switch,
Thank you.
one to
So
send
it's
from the switch
Los
to the
Angeles,
PC. So we're not
building
actually going
5.
to have a collision between our
And
PC
do you
and
have
the switch.
the entrance
But
number
there's
or
even a
any
bigger
code?
reason for this, and it has
No,
to do with our
there's no
Ethernet
code.
frame name
There's a
designation.
badge reader
I'll come back to that in a second.
for
So the
employees and
Ethernet will
contractors that
always
you
tend to
scan
go
and the
through.
doors open.
Fast Ethernet always means 100
Okay.
megabits per
Do you
second.
have any type of
Gigabit
access
Ethernet,
number
gigabit per
maybe?
second. 10 gigabit Ethernet, 10 gigabits per
No
second. And
access
40
number.
gigabit
No.
Ethernet, 40 gigabits per
Okay, so it's
second.
just the card
Now, I'll
reader
refer to Ethernet pretty
from the
broadly, and
main
other
entrance,
engineers
right?
are going to
Right.
refer to this very broadly as well. And just know that if somebody uses the term fast Ethernet, they're
And you may
specifically
have your
saying
name, please.
100
Yes, my
megabits
name
per
is
second.
Carlo. First name, it's
All right, fast Ethernet in modern
Karlo.
networks is not very
Last
fast.
name
And
Navarro,
at the time it came out, it was
Navarro.
fast. It was 10 times
And I'm
faster than Ethernet.
security.
So now typically we're just using
Thank
Ethernet as
you.
a broad
I have
term.
a telephone number that
And
we can get
if
in
we're
contact
saying
with you,
gig
please.
Ethernet or
Yes,
gigabit Ethernet,
it's
it's specifically meaning 1 gigabit.
818-507-8297.
Now, in order to get speeds of gigabit, 10 gig, and 40 gig, we must use full duplex.
818
We do not have a half duplex option for
507
these. They must use full duplex.
That's correct.
So when we talk about collisions in modern networks, is it possible
Do
to
you
have a
need my
collision on a
email?
gigabit Ethernet connection? Likely no. So does
No, go ahead and
CSMA/CD
watch it
apply here?
instantly.
No, it's
Yes. The switch and the PC are still listening to the wire, making sure that the communication channel is open before they send data. But it's likely that the communication channel is always going to be
Okay,
open in the
perfect. I will
direction that
send the
they're sending
request
it.
as soon as that
So in
if
modern
we put
networks,
this
we don't
transaction,
worry
the
too much
request
about
through,
collisions happening
you will
because we're
receive an
operating
email
that full
notification.
duplex
and with
communication.
the work order number, correct?
Yes, we will send you the work order number, yes.
Okay, thank you very much, Ro.
Please,
Let's
Victor,
talk
have a
about the
good night.
Ethernet frame. All right, so the Ethernet frame is the packaging on our data that we're sending. So we package up our data in a frame so we can send it across the network. And the frame is going to be specific to Ethernet so that the Ethernet devices on our network can read it and process it and decide what to do with it. So the information contained in the frame is going to allow us to do that. So this frame is going to contain a chunk of data, that's the gray part labeled packet, with a data link layer header. Right, so our data link layer header here, that's our Ethernet header. That's going to be the destination MAC address, source MAC address, and type. And then it's also going to have a footer, and it's going to have the FCS, or the frame check sequence. Our data here is the payload. That's the information that the frame is carrying. Typically, that's a packet, which is a layer 3 message. Sometimes it can be some layer 2 messages, which aren't a packet at all. Right? Because they're not layer 3. Layer 3 information is a packet. Layer 2 information is a frame. So let's look at the components here individually. First, we'll start with the MAC addresses, the source and destination MAC addresses. Those are going to be composed of two different components, a manufacturer ID and a serial number. They are 48 bits long, or 12 hexadecimal values. And the way this works is that the IEEE is the source of manufacturer IDs for MAC addresses. So if you are a manufacturer of network interface cards, you can apply to IEEE to get the Ethernet specification and a manufacturer ID that you can use in order to make network interface cards. Now, the network interface cards, when they are produced, they are encoded directly with a hardware address that is supposed to be unique in the world. Sometimes we get duplicate MAC addresses, which cause problems, but it's pretty rare. So what we do here is we get the manufacturer ID from IEEE, which is Institute of Electrical and Electronics Engineers, and then we use that to create our network interface cards and the MAC addresses. We do that by then generating a serial number to go along with our manufacturer ID. We combine those together and we get this 12 hexadecimal value MAC address. We can look up the manufacturer ID on the internet and find out who made a certain network interface card. That gives us an idea of the types of devices that are sending data. So the MAC address is an address that is burned onto the network interface card. We can change it in software, but that MAC address is part of the network interface hardware itself by design. The next component here is the type field. The type field is going to indicate what type of data is being moved here, or at least what protocol is being used to carry the data that's in the message, right? So if it's an IP packet, it's going to have a certain type code. If it's an IP version 6 packet, it's going to have a certain type code. If it's an ARP message, it's going to have a certain type code. So that type code is there to indicate to the network interface card and the operating system that's running on our device what type of message is about to come and which software system to pass it into. So if it's an IP version 4 message in our data, it'll have a certain type, and then our workstation will know to send that particular message, the data in our payload, it'll send that to a certain part of the software based on that type field. The last field on here is the frame check sequence, and this contains something called a cyclical redundancy check, or CRC. Now, a CRC is an algorithm, and what we do is we take the entire frame with the destination MAC, source MAC, type, and the data, and we run it through this algorithm, and it generates a 32-bit number. So the sending device will run this through its calculations. It will populate the FCS field with that number it generates, and then it sends the frame out onto the wire. When the receiving device gets this frame, it's going to look at that FCS value, do its own calculation just like the sending device did, and it's going to compare the two values. If the value in the frame is the same one as the receiving device calculated, we got a good frame, we're going to process it. If they're different, well, then we throw the frame away, and we hope that another protocol will resend that frame at another time. There is no mechanism in Ethernet to resend frames. We have to rely on other protocols like TCP up at the transport layer in order to make sure all those messages are sent and received correctly. But at Ethernet, at layer 2, we have no mechanism to determine whether a frame was successfully received or not. And that's okay. This whole system is designed to work together in order to achieve the end result. So the CRC is just validating that the frame sent is the same as the frame received. When we look at our payload, or the stuff we're carrying in our frame, there is by default a maximum transmission unit size, and that is 1,500 bytes of data can be carried by the frame. So that is our MTU, or maximum transmission unit. We can actually increase that if we need to. Now, in most networks, we're not going to do that. However, in data centers, specifically when we're working with storage area networks, we may want to increase that to make the hardware work more efficiently. So inside of data centers, we might increase this to beyond 1,500 bytes, and that would be a jumbo frame. But if our switches and our other devices don't support jumbo frames, they will actually just throw them away or to cause an error, and we won't process them. But if we have the capabilities to turn on jumbo frames, we may want to do that in a data center so that we can have a more efficient and faster operation of some of our hardware. The entire frame with the data itself that's included, this is called a protocol data unit, or a PDU. Now, you may hear this used in documentation and in instruction manuals that are more engineering related, but in day-to-day speak with other engineers, you'll almost never talk about a protocol data unit. You'll likely call it a frame instead, because that's what it is. But in engineering manuals and other documentation, you may hear this called a protocol data unit. Let's do a demonstration now and take a look at our MAC address on my Windows workstation. So here I am on a Windows 10 workstation. The way I take a look at my MAC address here is I open up a command prompt. I can do that one of a few ways. Right now I have it on my quick launch bar here, but I can also go into search windows here and type CMD, and that will bring up the command prompt. So once I have the command prompt up here, I can type the command ipconfig, and in order to see the MAC address, I need to issue an additional switch on here, which is the /all command. So ipconfig /all. And if I look now at my Ethernet settings here, it looks like I have two different Ethernet cards on here. My Ethernet 0 interface is the one that's connected. And this is my MAC address, 000C29FC70A5. So whenever I issue the ipconfig /all, the MAC address in Windows is listed as the physical address. Windows oftentimes likes to change the terminology. In fact, this is very, very, very common in data networking, where we use different terminology to describe the same exact thing. I'm not exactly sure why this happens, other than people who write the software have a different language than the people who actually do the troubleshooting of data networking, or it could just be meant to confuse people, for all I know. So anyway, this is my MAC address on my workstation, and again, I can find that by issuing the ipconfig /all command. All right, let's wrap up what we have here. We talked about CSMACD and saw that it was a legacy operation of Ethernet. We looked at collision domains. We looked at speed and duplex and saw how using full duplex communication resulted in less collisions or no collisions. Then we took a look at the Ethernet frame, and understanding the Ethernet frame is going to be very important to understand what happens in the next module, where we're going to talk about how Ethernet switches operate.
Well, the data security. Okay. Go ahead.
Let's continue our conversation about Ethernet with Ethernet switch operation. Our goals for this module are: first, we're going to talk about switch operation and what's special about it and how it works. Then we're going to talk about spanning tree protocol, which is a necessary protocol at layer 2 to prevent switches from stopping working. Then we're going to talk about VLANs and how important these virtual LANs are, or VLANs are. Then we're going to follow up and talk about power over Ethernet and its value and some of the details of the specification. The layer 2 switch. The layer 2 switch is a very common feature in Ethernet networks. In fact, it's the thing that makes Ethernet work. The important part here about the Ethernet switch is the MAC address table. It is the one table on a switch that tells us everything the switch needs to know in order to do its job. So here's how that works. So the MAC address table is nothing more than a list of port numbers along with the MAC address of each device connected to that port. So here we have a switch with 6 ports on it, so we'll populate our MAC address table with each of the port numbers. And then in order to make this a little bit easier to manage for this visual, I've substituted the 12 value hexadecimal number for 2 values, right? So there's just 2 numbers here that I'm using instead of 12 to make this a little bit simpler and cleaner. So how the MAC address table gets populated is inside of the switch on each one of the switch ports. There is something called an ASIC, or an application-specific integrated circuit. It's nothing more than a little chip, and all that chip is programmed to do is to read the destination and the source MAC addresses of our frames. So if my device over there, device A7, is sending a message into the switch, what will happen is the switch will receive that message, it will read the frame header, grab the source MAC address, and then populate the MAC address table. So right now I'm only showing you the source MAC address so we can see it populating the table. When all the devices do this, they will populate the MAC address table accordingly. Now, devices on a network, on an Ethernet networks, they're pretty much constantly sending out traffic to the switch. It might be just bogus traffic. It could be some traffic like ARP, where it's trying to find the MAC address of other devices. And it could be just other traffic from the operating system trying to figure out what's on the network. So our devices are always sending traffic out, typically, and the switch can read all those to populate the MAC address table pretty quickly. Then, when one of these devices, let's say device A7 over there on the far left, wants to send a message to device B3 in the upper right-hand corner, when it sends that message into the switch, the ASIC reads the destination MAC address, and then it consults the MAC address table, and it says, where is device B3? And here we found it attached to port 2. So now what will happen is the switch will build a small circuit in between port 6 and port 2 and send the message to device B3. If there's more than one message, that switch circuit will remain in place to send all the messages from one device to the other device. Once that's done being transferred, that circuit will be torn down so it can be reused for other things. At the same time, device C2 down on the bottom left might send a message to device 6E in the upper left corner of the switch. So when we send that message in, we do a MAC address table lookup again, see that device 6E is attached to port 1, we build our circuit and then send our message up to device 6E. And now both device A7 and C2 can communicate with 6E and B3 at the same time without impacting each other's conversations. So the switch is a very efficient method of passing traffic between devices on a network. And this is basically how Ethernet works here. Using the MAC address table, we're able to find devices on the switch and forward the messages accordingly. Let's talk about broadcast messages now. Now, broadcast we've talked about already when we talked about IP addresses at layer 3, and there is a broadcast address in IP addresses. However, that is not what we're talking about here. As a matter of fact, broadcast IP addresses are not used very often at all. They were intended to have a purpose, but they really just aren't used very much. At layer 2, though, broadcasts are used constantly. And this is how the broadcasts work. If we take a look at our Ethernet frame again, the destination MAC address field, if that is all Fs or all binary ones, what that means is this message is destined for every device connected to the layer 2 network. So let's take a look. This is a layer 2 broadcast address of all Fs in the destination MAC address field. So here's the definition. When the destination MAC address of the frame is all Fs, the frame has sent out all active interfaces on the switch except for the interface that received the message. Let's take a look at how that works here. Now, I've simplified my broadcast message again to be just 2 Fs instead of 12. When the switch receives the frame with a destination MAC address of all Fs, that frame is forwarded out all of the other interfaces, except the one that it was received on. So device A7 sent the broadcast, it was received on port 6. We send it out all active ports except port 6, which means all the other devices get that message. So a broadcast domain then is a group of network devices which will receive a layer 2 broadcast message. So let's move on to a demonstration now. We're going to take a look at the MAC address table on a switch. So the drawing that I'm going to use here, I actually only have 2 devices connected to my switch right now. One is on port 3 and the other is on port 6. I've listed the MAC addresses for each of the devices here. So on port 6, we should see a MAC address ending in 70A5. And then on port 3, we should see a MAC address ending in A08D. These 2 workstations are connected to a Cisco Catalyst 2960 switch. This is an older switch. It's a 100 megabit switch. However, it does do everything that we need it to do to see the MAC addresses and other Ethernet stuff that we're going to take a look at. So this is the drawing we're looking at. Remember, we're looking for 70A5 on port 6 and A08D on port 3. So let me move over to my Windows 10 workstation. So this is my Windows 10 workstation. Let's open up a command prompt and take a look at the IP configuration information here so we can see our MAC address. And here we do have the physical address 000C29FC70A5. Now, in order to get on the switch, now you're only going to be able to do this at home if you have your own switch and you're connected via the console port on that switch. So if you don't have that, that's okay. Just follow along and watch. You're not going to be able to do this directly on your PC because we're actually connecting to a remote device. If you were in a real setting looking at your switch's MAC address table, what you would do is you'd probably SSH to that switch. But since I'm sitting right next to this switch with the cable connected, we're just going to connect to it with a serial cable. So to do that, I open up the PuTTY application and I can connect to my switch. Now, if you want to learn more about how all of this works with connecting to the switch, to do the configuration, to look at the MAC address table and whatnot, you can really do a much deeper dive of this by taking a look at my Certified Cisco Network Associate course, or courses. It's a series of about 22 courses that I go do a very deep dive into how all of this network technology works, and then you also learn how to configure all the components. For now, though, we're just on my switch here. Let's do a show MAC address table. And when I do the show MAC address table, there's a bunch of entries in the beginning here, and those are related to the switch itself, and we can largely ignore those. The ones that we're interested in here are at the bottom, these dynamic list here. As a matter of fact, I can shorten the list by doing show MAC address table dynamic, and it'll just show me the ones that I want to see here. So right now we see there's MAC addresses associated with port F03 and MAC addresses associated with port F06. So we're looking for the MAC address at N10-008, and that is associated with port F06, just like my drawing showed. And then the other one here ending in A08D, that's associated with port 3, just like I've shown in my drawing. Now, you might notice here that there's actually 4 MAC addresses listed. There's these other 2 ending in 41C9 and 41CC. Now, these 2 MAC addresses are actually a byproduct of how I have this configured. In the previous course, we talked about virtual networking, and this Windows 10 PC that I'm working on right now is actually a virtualized computer. The virtualized computer has a virtualized network interface card. And that virtualized network interface card is directly connected to a real Ethernet network interface card. So that's why we're seeing 2 different MAC addresses here. My workstation itself has a virtual MAC address that ends in 70A5, and the physical device has a MAC address that ends in 41C9, and both of these show up in my MAC address table simply because of the way I have it set up. We can largely ignore the physical connection here because we're working exclusively with my PC that's connected. The MAC address table, by its very nature, can have numerous MAC addresses associated with each port because we might connect another switch to a port on the switch, and that switch that we're connected to is going to have lots of MAC addresses associated with it as well. So just be aware that we can have more than one MAC address associated with each port. Let's move on and talk about connecting switches. Switches are kind of neat because we can daisy chain them together, or we can put them in a loop. And what that means is we're just going to have one switch connected to another switch with an Ethernet cable. And this is going to make the switch work just fine. So when we look at broadcast messages, when we connect switches together, this is kind of what we have to take a look at. So a broadcast message, if I send it from the blue PC, in this case, there's only two devices here. It's only going to be sent to the maroon colored PC. If the maroon colored PC sends out a broadcast, it's only going to be sent to the blue one. If I add another PC on here, we just double the number of messages that the switch sends out here. So now both the maroon and the green PC get a message. Same thing happens if the maroon PC sends out a message, we get a broadcast to both the blue and the green. And if the green one sends it out, of course, it's going to go to both the blue and the maroon. Well, what if we add another switch here? If we add another switch here, what's going to happen is basically the blue device sends out a broadcast message. It gets sent out all active interfaces, including to the one that's connected to the other switch. The other switch then receives it and sends it out all active interfaces. That means that all devices in this broadcast domain receive the broadcast message. This is very, very, very important for Ethernet to work correctly. Sometimes devices don't know about other devices on the network, and we can send a broadcast message to learn about them. This is true regardless of which device is sending it. Now we have all four devices sending broadcast messages into the system. And although this looks like it's creating a lot of traffic, the reality is this is just the normal way for Ethernet to behave. However, this can become problematic if we connect two switches together with two links. If we connect two switches together with two links, and we're not using any additional protocols, what can happen here is if the blue device sends out a broadcast message, that broadcast message is then going to be sent out all active interfaces, which means we send the messages to maroon PC as well as the other switch on both interfaces. Now, both interfaces on the lower switch receive that broadcast message and then send it out all active interfaces, including back to the switch that sent it originally. And then this process is going to happen again when it gets to the top switch. It's going to send that broadcast message out all active interfaces, send the messages back out the opposite interface down to the bottom switch, and now we have this loop, right? So now we have a loop where broadcast messages are permanently being sent in this network. They will never, ever, ever stop. And devices will continuously broadcast. So the devices aren't going to stop broadcasting messages. They're going to keep broadcasting more messages. So now we have the green device sending messages as well. And you can see this is starting to get very clogged up. And what will happen eventually, once all the devices are sending messages and we have too many broadcasts in the system, it's going to clog up all the links. It's going to overwhelm the switch, shut it down. It's creating something called a broadcast storm. And we have to prevent this in Ethernet, or our networks just won't work anymore. It's very easy to accidentally connect two switches together. And the way we solve the broadcast storm is we shut down one of the ports. So what we hoped to achieve by connecting the two switches together with two links to create some more bandwidth actually doesn't do what we want it to do, and we end up having to implement something called Spanning Tree Protocol, or STP. And Spanning Tree Protocol will actually just shut down one of the links and prevent it from being used at all. That way, when a broadcast message comes into the switch, it never gets repeated out the interfaces and sent back to the switch that sent it. So this is going to prevent the broadcast storm. If for some reason one of the links goes bad and gets disconnected, Spanning Tree Protocol will kick in, it will unblock the link, and it'll allow the traffic to flow. So we do get some redundancy with this, but we don't double the bandwidth of our link. We need a different protocol to do that. Spanning Tree Protocol is going to work no matter how many switches we have here, or almost no matter how many switches we have here. If we have 3 switches connected together like this, the job of Spanning Tree Protocol is to figure out which port to block, right? We're only going to block one of these ports, and we need to figure out which one to block, and that's the job of Spanning Tree Protocol. Well, let's do a demonstration now and take a look at Spanning Tree Protocol. I have this lab set up here with 3 switches, switch A, B, and C, and they've connected together just as I've shown here, with F01 on switch A connected to F02 on switch B, F01 on switch C connected to F02 on switch A. This creates a loop, and if we didn't use Spanning Tree to block one of these ports, that would create a broadcast storm and this network would shut down. So let's move over to my Windows workstation and take a look. So here I'm at my Windows 10 workstation. I've taken a screenshot of that drawing so we can kind of see how it's all connected. This will be important as we take a look at the different switches. So I'm going to open up my PuTTY window here. Now PuTTY again is the utility I use to connect to the serial port of my workstation so I can investigate what's on the switches and configure them. Right now, let's connect to switch A. So I'm on switch A, and if I do the command show spanning tree, that will show me information about how spanning tree is configured. It's going to show me all of the active ports, and we're interested in F01 and F02 here. And right now, these are both showing that the status is forwarding. FWD means forwarding, which means that those interfaces are passing traffic and not blocking it. So on switch A, both interfaces on switch A are forwarding traffic. Let's go take a look at switch B. So I just need to move my cable over to the other switch so I can take a look at that. And if I just press the enter key now, it'll jump me over to switch B. Let's get into the right mode here and do show spanning tree protocol again. This time we can see that port F01 is in the forwarding state. So that's the port that's going from switch B to switch C. That's forwarding. And then port F02 is in the blocking state, which means that this port on switch B here, let's see if we can draw on there. So this port on switch B is blocking here. So let's take a look at switch C and see if anything else has changed there. So we'll move my cable over to switch C and do show spanning tree. And here we should see that both interfaces are in the forwarding state, meaning that the only interface that's blocked is the one between switch A and switch B, and it's specifically blocked on port F02. So what this means is that we have a complete network. Any traffic that's on switch A has a path to get to switch C and to switch B, but there is no loop in this network. Now, if for some reason I disconnect the link between switch B and switch C, so let me do that here. I'm going to just pull the cable between switch B and switch C. So I'm going to pull F01. And we should see a message on switch C saying that one of the ports went down here. So that's exactly what happened. It says interface fast Ethernet 02 changed state to down, which means that that interface is no longer up. Now it's going to take a few seconds for spanning tree to reconverge here. So it's going to take up to 45 seconds for this to reconverge. So we're going to speed this up. And now it appears to be reconverged. Let's take a look at show spanning tree now. And now we should see that all of the ports are in a forwarding state. So here we have switch C, port F01 is forwarding. If we go to switch B, Move my cable over and go to switch B and do show spanning tree protocol here again. We can see that port F02 is forwarding now. It is no longer in that blocked state, so we can erase that note here. And let's put an X here for this link being down. And now if I move over to switch A, we should see both ports F01 and F02 in the forwarding state. Show spanning tree, and we see that port F01 and F02 here are both in the forwarding state. So what this means is when we disconnect the link, spanning tree reconverges for us so that we no longer have that blocked port on switch B, F02. And that allows us to pass traffic now again continuously between switch A, switch C, and switch B. Next, let's take a look at port aggregation, which is something that, we're going to solve the problem of spanning tree. We want some extra bandwidth maybe between these two switches. So we want definitely to have two links connecting the two switches, but we need a special protocol to do that. And that's where something called port aggregation comes in. Port aggregation is also called a port channel, an ether channel, a channel group. There's lots of different names for it, but it all has one thing in common, and that is that we're taking two or more links between two switches, and we're bonding them together to behave as if they were one single link. That way we get extra bandwidth, we get some redundancy as well. The protocol we use to do that is called LACP, or Link Aggregation Control Protocol. This is the open source version of this, and you'll oftentimes see it used when we're doing port aggregation or ether channel in a network. Let's move on and talk about VLANs. So we're going to introduce VLANs here. VLANs, if I had to characterize something in data networking that is one of the most important topics, VLANs would be it. If one can understand VLANs and IP addresses really well, you can understand almost anything in data networking, and you can have a really good career in troubleshooting and support. Well, let's do a demonstration now and take a look at spanning tree protocol. I have this lab set up here with 3 switches, switch A, B, and C, and they've connected together just as I've shown here, with F01 on switch A connected to F02 on switch B, F01. Let's do another demonstration where we go into a switch and configure a VLAN. I'm going to jump over to my Windows 10 workstation here. We're going to open up PuTTY again and connect to my serial port so we can do some switch configuration. On switch A, and right now if I do show MAC address table, I should be able to see that there is a connection on port 3 and port 6. So let's change the VLAN of our device on port 3 to something else. So if I go into my configuration mode and then I say interface fast Ethernet 0/3, that will get me into the configuration of that particular interface. And then what I can do is I can issue the command switch port access VLAN, and then I can tell it a different VLAN number. Now, right now, this is connected to VLAN 10, and I know that because in my MAC address table, I have the VLAN number listed here, and the VLAN number listed for port F03 is 10. So if I want to change that, let's change it to VLAN 20. And I hit enter here, and now that changes that port. Instead of being on VLAN 10, now it's on VLAN 20, so now it's in a separate broadcast domain. So if I do a show MAC address table again, now what I should see is that port F03 is now associated with VLAN 20 instead of VLAN 10. If you want to learn more about configuring VLANs and trunk links on switches, you should definitely check out the Cisco Certified Network Associate series. It's 22 courses long, so it's an extensive series of courses, but I go through all the details of what you need to know on how to configure network devices to do routing and switching, among other things. Another thing we can do with switches when we're troubleshooting networks is we can do something called port mirroring. So let's say that we have a call to the help desk from a user saying, hey, I'm having troubles getting to this web server, something's going on, I'm not sure what's happening. So what we can do then is we can come in with a device to sniff the traffic. So we can add this device in and say, all right, let's take a look and see what's happening with this. So we do a port mirror where we just take all the traffic that is coming in or leaving an interface and we mirror it to another device so we can troubleshoot that traffic. So here we go, we've mirrored the port. Now all the traffic coming from the user's device going to the web server is getting mirrored to this other device where we can set up a traffic capture and then use that to analyze the traffic and see what's going on. We would likely use a product called Wireshark, which is a freely downloadable protocol analyzer to analyze that traffic. And we actually have courses on Wireshark here at Pluralsight. I've done several courses on Wireshark. My good friends Chris Greer and Betty Dubois also have great Wireshark courses out there that I highly recommend checking out. Let's wrap up our Ethernet conversation here, at least for the moment, by talking about power over Ethernet. Now, power over Ethernet is really, really useful. When we have devices on the network, like PCs and servers, those take a lot of power, so we need to plug those into the wall. However, when we have something like a wireless access point or a voice over IP phone, those don't take a ton of power, and we have this cool protocol called power over Ethernet. And power over Ethernet allows us to power devices directly from the switch. Now we need a very special switch to do this, and when we have that special switch, we can plug in our device, configure the port to have power going to our device like a phone or an access point, and now we don't need to have a separate power cord going to each one of those devices. There are several different protocols we can use here. One is 802.3AF. This came out in 2003 and delivers 15.4 watts of direct current. Let's do another demonstration where we go into a switch and configure a VLAN. I'm going to jump over to my Windows 10 workstation here. We're going to open up PuTTY again and connect to my. Let's continue. Another thing we can do with switches when we're troubleshooting networks is we can do something called port mirroring. So let's say that we have a call to the help desk from a user saying, hey, I'm having troubles getting to this web server, something's going on, I'm not sure what's happening. So what we can do then is we can come in with a device to sniff the traffic. So we can add this device in and say, all right, let's take a look and see what's happening with this. So we do a port mirror where we just take all the traffic that is coming in or leaving an interface and we mirror it to another device so we can troubleshoot that traffic. So here we go, we've mirrored the port. Now all the traffic coming from the user's device going to the web server is getting mirrored to this other device where we can set up a traffic capture and then use that to analyze the traffic and see what's going on. We would likely use a product called Wireshark, which is a freely downloadable protocol analyzer to analyze that traffic. And we actually have courses on Wireshark here at Pluralsight. I've done several courses on Wireshark. My good friends Chris Greer and Betty Dubois also have great Wireshark courses out there that I highly recommend checking out. Let's wrap up our Ethernet conversation here, at least for the moment, by talking about power over Ethernet. Now, power over Ethernet is really, really useful. When we have devices on the network, like PCs and servers, those take a lot of power, so we need to plug those into the wall. However, when we have something like a wireless access point or a voice over IP phone, those don't take a ton of power, and we have this cool protocol called power over Ethernet. And power over Ethernet allows us to power devices directly from the switch. Now we need a very special switch to do this, and when we have that special switch, we can plug in our device, configure the port to have power going to our device like a phone or an access point, and now we don't need to have a separate power cord going to each one of those devices. There are several different protocols we can use here. One is 802.3AF. This came out in 2003 and delivers 15.4 watts of direct current power to our device. And then later on in 2009, we have 802.3AT, and this is 25.5 watts of direct current power that we can give to our devices. This is what's needed for more modern gear. This is called PoE+. So we have PoE at 15.4 watts and PoE Plus at 25.5 watts. Let's wrap up what we've talked about in this second module about Ethernet. We talked about switch operation. We talked about spanning tree protocol and took a look at how the spanning tree protocol blocks ports. We looked at VLANs and saw how we configure VLANs on a switch. And last, we looked at power over Ethernet. I hope you have a much better understanding of how Ethernet works now. We're going to go on and use our knowledge of Ethernet and Layer 2 broadcasts now to understand more about how Layer 3 works with routing. Hi everyone, I'm Ross Bagurtis, and welcome to this next module where we're going to talk about routing IP traffic. Our goals for this module are to do a very brief review of the OSI model again so we can stay focused on what layer of the OSI model we're talking about for different protocols and different components in networking. We're going to introduce network layer communication so we can see what's happening at layer 3 when we're using IP to send traffic between one device and another. To do that, we're going to need ARP, or Address Resolution Protocol, so we'll explain that in detail. ARP is a Layer 2 protocol that works directly in conjunction with Layer 3 and Internet Protocol, or IP. We're then going to describe the purpose and the use of the default gateway to route traffic between unique Layer 3 networks. We're going to describe how IP routing works and how to build routing tables on routers. And last, we'll demonstrate Traceroute. Traceroute is a nifty utility that can show us all of the routers that exist between my workstation and some device out on the network or on the internet. So when we're looking at the OSI model here, we're talking about routing IP traffic. We're going to make use of the bottom 3 layers, the physical layer, the data link layer, and the network layer. The protocols that are going to be interacting together are going to be some Layer 2 protocols and some Layer 3 protocols. The reason for this is that at the data link layer, that's responsible for moving traffic from one device to another device in small increments. Now, in order to get from my workstation over to the server, I have to go through lots of little increments of networks that are mostly Ethernet, but some are different. And if you remember, Ethernet is a Layer 2 network. We put our information inside of a frame, and then we forward that frame onto a switch, and the switch is able to create a connection inside the switch between one device and another. So Layer 2 here is critical for passing traffic between our devices. However, in order to get traffic from one device on the internet to the other device, from our client to our server, we need to make use of all those individual little data link layer connections, but we also need some map, some bigger picture utility that's going to allow us to get across the entire internet efficiently. And that's where the network layer comes in with Internet Protocol. So here we're going to use routers in order to move our traffic from one segment of the network to another. The router that I've drawn here is just a home wireless router. In the real world, in a business, we're going to draw a router as a circle with these arrows pointing in and out of it. And the path between our workstation and our server on the right-hand side there is going to be full of routers. This is going to be interacting directly with Layer 2 because here is a device on our network. This is our cable modem for our internet service in our home. This is a Layer 2 bridge, and all it does is it converts Ethernet frames into DOCSIS frames. So it takes the packet out of the Ethernet frame and puts it into a DOCSIS frame. DOCSIS is the protocol that cable modems use in order to communicate between the cable modem and the internet service provider. So we're just going to pull the packet out of the frame and put it into a new frame. That's all this layer 2 bridge does. All these devices are very critical in our network because they're going to help us move the traffic from one end of the internet to the other. The internet itself is full of routers, and in our last demonstration, we're going to use traceroute to see all the routers between our workstation and a server that we try to reach. So let's keep this simple and start looking at a basic network. So here I have a very simple network. I have two devices, 10-0-0-10 and 10-0-0-20, and they're connected to a router, and that router is connected to the internet. When I am on my local workstation, whenever I'm working there, it's going to be sending traffic locally, so between 10-0-0-10 and 10-0-0-20 and my router. And it's also going to be communicating with the internet, or at least attempting to communicate with the internet. So when I'm looking at this, there's going to be two different modes that I'm operating in. One, I'm going to have to use the router to forward the traffic. The other one, I'm just communicating locally between two devices. So let's take a look at all the components that make this kind of communication work. We're going to start by looking at just a conversation between our two internal devices here, 10-0-0-10 and 10-0-0-20. We're going to start with the IP packet. So when we try to send a ping message, which is what we're going to try to do here, we're going to ping from 10-0-0-10 to 10-0-0-20. We're going to be using the ICMP protocol, or Internet Control Message Protocol. And that protocol is what ping uses to send the message and get a response. So that ICMP data is put inside of an IP packet, which is composed of a source IP address, a destination IP address, a time to live, as well as quite a bit of other information in order to properly pass that packet. I'm leaving the other information as just other because it's not critical to understand how this process works. The other information is going to be critical when you do deeper dives into Internet Protocol and see how it works. This IP packet then is going to be put inside of a layer 2 frame. And the layer 2 frame is going to change often as it moves across the network. That layer 2 frame, we've looked at this before, it has a destination MAC address followed by a source MAC address, and then the layer 3 protocol that it's carrying, which in this case is IP version 4. We put all that inside of our message here, and that message can go then onto the workstation and get sent between our two devices. So let's look at the detailed process of how this happens. We start with ICMP on 10-0-0-10. I'm going to type in ping 10-0-0-20. That's going to allow us to generate an IP packet header and fill in our source and destination IP addresses. Additionally, we're going to fill in the time to live value here, which is going to be 128. That value is set by the operating system, and it can range between 1 and 255. Most operating systems defaulted to 128, and what that value does for us is it's a counter, and every time that packet goes through a router, that TTL, or time to live, will be decreased by 1. That way, if we go through 128 routers, the packet says, yeah, that's too far away for me, I'm just going to throw it away, just not worth it anymore. What this really does is it helps routers who may have accidentally configured themselves in a loop, so that if it gets into that loop, the packets won't live there forever and they'll eventually just die out. Anyway, so that time to live value, we're going to see what happens with that later on when we look at sending a message on the other side of the router. For now, we're just communicating within our own local Ethernet segment here. So once we have this generated, we can then put this message in a frame. So we put the packet inside of our frame, we fill in our source MAC address, which is the MAC address of our workstation. Our layer 3 protocol here is IP version 4, and we need to know our destination MAC address, which is the MAC address of 10-0-0-20. The problem here is I don't know what that MAC address is. My workstation doesn't either, so we have to figure out what that is. That's where ARP comes in. Address Resolution Protocol is going to come in and save the day. So here's how ARP works. So we're going to put our message on hold here for a second. So we've built most of it. We just need to know the destination MAC address. So before we can fill in that, we need to create another frame here. And this time we're going to say, hey, who has 10-0-0-20? And this is an ARP request saying, hey, 10-0-0-20, if you're out there, send me your MAC address. That's going to go right inside of a frame header. We can fill in our source MAC address because we know that. We can fill in our layer 3 protocol, and in this case it's not actually a layer 3 protocol. ARP is a layer 2 protocol, so we don't actually have layer 3 here, but we're going to tell the frame header which protocol is being carried in the data section. And then for our destination MAC address, I'm going to put all Fs in here because I want every single device on the layer 2 network to receive this message and be able to answer the question, who has 10-0-0-20? If the device doesn't have it, it can throw this message away. If a device does have the MAC address for 10-0-0-20, it'll respond. So we put that frame inside of our message here. We send it out onto the network. It goes out to all the devices except the sending device. The device that has 10-0-0-20 says, hey, I have this MAC address because it's me. I know what that is. So we hang on to our source MAC address from 10-0-0-10. We then create a response to our ARP request. We say, yep, here we go. Here is the MAC address for 10-0-0-20. We fill in our destination MAC address because we know who sent it to us. We fill in our source MAC address because we know what our own MAC address is there on 10-0-0-20. We then send that on the wire. Send MAC address because it's me. I know what that is. So we hang on to our source MAC address from 10-0-0-10. We then create a response to our ARP request. We say, yep, here we go. Here is the MAC address for 10-0-0-20. We fill in our destination MAC address because we know who sent it to us. We fill in our source MAC address because we know what our own MAC address is there on 10-0-0-20. We then send that on the wire over to 10-0-0-10. 10-0-0-10 then pulls that frame out, looks at the ARP reply, says, okay, the destination MAC address is right here. Now I can take my ping message that I wanted to send before, fill in the destination MAC address, put that out onto the wire, and say ping 10-0-0-20, and now I'm able to forward that message directly onto that device. You might say, but Ross, why don't we just send it to the broadcast address? And the reason is that would get messy. That would defeat the purpose of the switch. It means all the traffic we'd send out would all go to all the devices. And now our switch could easily get overwhelmed with traffic, and it would really defeat all of the efficiency we have built into it. So ARP really saves the day here. Additionally, ARP is going to maintain something called an ARP cache or an ARP table. That ARP table is going to be a mapping of a layer 3 IP address to a layer 2 MAC address. So my workstation will maintain this ARP cache, and the next time we need to send a message to 10-0-0-20, we're not going to have to send an ARP message out again. We can just look in our ARP table and see that we already have that information without having to ask for it. Now that ARP cache is only valid for a few minutes or maybe even only 90 seconds depending upon the operating system. After that time, the ARP entry will be removed and the workstation will have to resend an ARP message out to get the updated MAC entry. And that's allowing for devices to change their IP addresses on the network, because when you change the IP address, it's going to be associated with a new MAC address, and ARP will have to figure out what that is. Now, something to note here is that we have looked at MAC address tables on switches, and the MAC address table on a switch takes a layer 1 interface, a physical port that we're plugging a cable into, and it maps that physical port to a layer 2 address or a MAC address. The ARP table is located on devices that have layer 3 capabilities and is going to map a layer 3 address, a layer 3 IP address, to a layer 2 MAC address. So these two tables have very specific purposes. They are not the same as each other. And when I teach students this, oftentimes this gets confusing because we're looking at MAC addresses. Sometimes we need to look at both the ARP table and the MAC address table, but just know they're not the same table. do a quick demonstration here and take a look at our ARP table as well as our IP configuration information. So here I am on my Windows 10 workstation. I'm going to open up Command Prompt, and we're going to take a look at my IP configuration. So I can just issue the IP config command. It tells me my workstation's IP address here is 10.0.0.10. If I look at my ARP table, now I can look at my ARP table by issuing the command ARP-A, and that will show me all of the IP address to MAC address mapping. Now there's one entry in there, 224.0.0.22, which is used by a protocol called IGMP, or Internet Group Management Protocol. This is something Windows is using to discover information about other devices on the network. So this isn't going to be useful for us if we want to send a ping message to 10.0.0.20. So if I come back and send a message to 10.0.0.20, we're first going to start to create that message, not have the MAC address. We're going to go get the MAC address and then create our packet and send it. And you can see how quickly that all happened, right? It took me almost 10 minutes to explain that process, but here it's happening in just a few milliseconds. So if I then look at my ARP table, ARP-A again, now I have a specific entry in there for 10.0.0.20, and it is 000C2974A08D. So that is the destination MAC address that I'm sending to here. So that is how ARP works. This is my ARP cache. As that entry times out, it will send out new ARP requests to rebuild that table. Let's continue on our conversation about how IP routing works. We actually haven't even gotten to IP routing yet because the understanding of ARP is so important to understand how IP routing works. Now I've changed up my network a little bit here, and instead of having the internet on the right-hand side, I've replaced that with another PC on the 192.168.10.8 network. So let's take a look at how this works now when we try to send a message from 10.0.0.10 to 192.168.10.8. So we're going to first build our packet, put our source and destination IP addresses in there. We're going to put that then inside of our frame, and we're going to start to build our frame. We know, once again, our source MAC address. We don't know our destination MAC address yet. So we're going to have to find out what that is. So what do we do here? Do we send an ARP request and say who has 192.168.10.8? We absolutely cannot do that. We cannot ARP for the destination IP address because it's not on our own local network. Remember, earlier I said ARP messages cannot be sent through a router. So we're not going to be able to send the message out asking who has the MAC address for 192.168.10.8. Instead, what we're going to do is we're going to consult our routing table on our PC. The routing table on our PC is going to know how to reach two things typically. It's going to know how to reach our local network, 10.0.0.0, and it's going to have a route for everything else, which is going to be our default gateway or our default router. A gateway is a router. They're the same thing. So the default gateway is the default router. In this case, it's 10.0.0.1. So when my PC is trying to send a message to an IP address that's not on my local subnet, it will automatically look up the default gateway's IP address, and then we're going to do an ARP request for the default gateway, in this case 10.0.0.1. So we'll send out our message here saying who has 10.0.0.1. It's a broadcast, so all the devices on the 10.0.0 network get it. The router says, yep, that's me. I have that MAC address. Let me build a message and send it back to you. Here's my MAC address. Now we can take our original message with our ping in it, going to 192.168.10.8. We can now fill in our destination MAC address of the router. So in the beginning of this conversation about routing, I told you that we're sending messages from one device to another. So here we're sending it from the PC to the router, and our frame is what accomplishes that. So we put in our source and destination MAC addresses of our frame. We then can put that out onto the wire because now we know the destination MAC address of our default gateway. That gets sent to the router. The router then opens up that message, says, hey, this message is for me. That's my destination MAC address. We throw the frame header away and we open up the packet. Once we're in the packet, we look at the destination IP address and say, hey, do I know how to reach that? And the way that the router does that is it looks inside of its routing table. So on the router, we can issue a command called show IP route, and that will show me the routing table that is for that router. And this router knows about two different networks. It knows how to reach our source network of 10.0.0/24. That's connected to Fast Ethernet 0/0. That's just the name of the interface that we send it out of. And then we have 192.168.10.0/24. And that's connected to interface Fast Ethernet 0/1, a different physical interface on the router. So what we do now is we take our destination IP address and we compare it to what the router knows how to reach. So here we look at, is 192.168.10.8 on the 10.0.0.0 network? Nope. Is 192.168.10.8 on the 192.168.10.0/24 network? Yes, it is. And if you remember in our exercises for IP addressing from our first course, one of them I had you do is determine the network associated with a specific host. Remember, there's all zeros in the host portion of a network address. So all we're doing here is we're saying with a /24 mask, 192.168.10.8 is on the 192.168.10.0 network. That's connected to Fast Ethernet 0.1. So now what we can do is we can start building our frame again. First, though, before we do that, we have to decrease the time to live value because we've just processed it through a router. So our time to live is going to decrease by 1. So now we're going to start to construct our frame header. We know what the source MAC address is. It's the source MAC address from F0/1. We don't know the destination MAC address, so we have to put that message in the queue for a second while we go use ARP to find out who has the MAC address for 192.168.10.8. We send that message out F0/1. My device says, yep, that's me. I have that MAC address. So I put the MAC address in a message and I send it back to the router. The router adds it to its ARP cache. Now we can fill in our destination MAC address and put this message out onto the wire. Send it over to 192.168.10.8. And now 192.168.10.8 can reply to my ping. So this is the very slow version of this process of my message leaving 10.0.0.10, getting sent to the router through the frame. If you noticed, my IP packet was unaltered except for the time to live. I didn't mess around changing IP addresses. I let the frame figure out how to reach my router. Then the router looked inside of my frame at the packet header to find out where it should send it. Once it found out where to send it, it constructed a new frame and forwarded that message on. So the frames, when we're sending packets across the network, the frames are just little temporary vehicles for our packet to get moved from one router to the next. Let's take a look at IP routing. So whenever we have a network, usually we're going to have more than one router. As a matter of fact, the internet is full of routers. It's really what makes the internet work, is all these routers. So there's routers and there's connections between the routers. So here I have routers A, B, and C, and I have 4 unique networks. Connected to router A is 10.0.0.0/24. And then connected also to router A, the connection between router A and B is 172.16.0.0/30. Then I have 172.16.0.4/30 connecting routers B and C together. And then last I have 192.168.10.0 connected to F01 of router C. So by default, router A knows how to reach 2 networks, 10.0.0.0 and 172.16.0.0/30. And I've listed the interfaces that those are connected to right next to it. This is effectively what the routing table looks like. It's the networks that the router knows how to reach. Router B is going to know how to reach two networks, 172.16.0.0 and 172.16.0.4, both of those /30. And then last, router C knows how to reach 172.16.0.4/30 and 192.168.10.0/24. So if I try to send a message though, so if I say on 10.0.0.10, let's ping 192.168.10.8, and I send that message out onto the network, the first router receives that and it looks up in the routing table and it says, I don't know how to reach that at all. I have no route to that. So what the router does is it throws the message away. It says, I don't know how to reach it. I'm going to throw it away. Occasionally, the router will send a message back to the sending device saying, yeah, I don't know how to reach that. It all depends on if the router is configured to send an ICMP message back to the sending device saying, yeah, I don't know how to reach that. So what do we need to do? We need to build the routing table. So we're going to build this statically. We're going to manually configure each of the routes. So the idea here that we want is that router A needs to know about all the networks that are not directly connected to it, as well as how to reach those. So one of the networks that router A does not know how to reach is 172.16.0.4. So let's add that to the routing table and say we'll reach that by going to router B. So we manually add this entry in and say, hey, if I'm trying to reach this network, send it over to router B. And the next hop address that we would send that to is 172.16.0.2, which is router B's F0/0 interface. Then we need to know how to reach 192.168.10.0, and that also gets sent to router B. We can't send it to router C because we're not directly connected to that, but we can send it to router B because we are directly connected to it, and then we'll let router B figure out what to do with it. So we'll send our message then on to router B. So now router B needs a complete routing table. It needs to know how to reach 10.0.0.0/24, which gets sent to router A. And it needs to know how to reach 192.168.10.0/24, and that gets sent to router C. And then last, router C needs to know how to reach two networks, needs to know how to reach 10.0.0.0/24. We can send that traffic to router B, so router B can get it over to router A. And also 172.16.0.0/30, which is also connected to router B. So now we have a complete routing table. When I try to send my message now to 192.168.10.8, it gets sent to my default gateway, which is router A. Router A looks up in its routing table and says, do I know how to reach this? And says, yep, I send that message to router B. So it puts it inside of a frame, sends it over to router B. Router B looks up in its routing table and says, hey, do I know how to reach this network? It says, yes, I do. I send it over to router C. So we decrease the TTL by 1, put it in a new frame, send it over to router C. Router C then looks up in its table, says, hey, do I know how to reach 192.168.10.8? Say, yep, it's directly connected to my fast Ethernet 0/1 interface, and we can send the message directly to the device then. Then 192.168.10.8 can reply to the ping message, and we have a path all the way back. Router C needs to send this message to router B. Router B needs to send this message to router A. Router A is directly connected to the 10.0.0.0 network, so we can send it right onto the intended device. So this is the idea of IP routing. Every single router has a little map of how to reach all of the networks. As long as that map is maintained correctly and all the links are up, we can send traffic between our two devices. The internet is full of routers. When we are in an enterprise business or a large enterprise business, we have lots of routers there as well. Keeps all of our traffic separated and moving very efficiently. In order to get IP routing to work right, we need to have more sophisticated options than manually configuring. Let's look at how we do that. So IP routing can happen one of two ways. We've talked about static routing. That's where I manually enter in my routes. The trouble with static routing is that once I enter the route in, it's permanently in there and it's unchanged unless I go manually change it in the future. Another option I have here is something called dynamic routing. And dynamic routing is going to use a routing protocol in order to build the routing tables themselves. And there's several different protocols we can use here. One of them is RIP, or Routing Information Protocol. This is a very old one that's not used at all anymore. It's very slow. And it's not very good.
Hello, the data security.
However, it was
I
used
have
I
back
think it's
in the
security
80s
today.
and early networks.
CompTIA here at Gate A and critical system to the meeting.
Networks.
I'll be up there right now. What I need to do? Do I need a form or something?
Today, though, we need
Oh no, just escort him, walk him into
networks.
the front of B5 right by the hydrogen tanks.
Okay, I'll be right there.
Thank you.
Hey, good.
Routing
Have a good day, man.
I am available on Cisco devices. It is written as a
Thank you,
publicly
Naval.
available
No problem.
protocol, so really any company can implement this. However, EIGRP is in some cases kind of on its
Bye,
own.
okay, Mr. Davis, hello.
Hello, the data security. I have CompTIA here at Gate A coming in.
Very
Back
often.
okay, we'll try to get an outlet done as soon as possible, but it is during our lunch hour right now, and we're stretched a little thin right now.
All right.
Okay.
Enterprise
Thank you.
networks and networks of big businesses. There's one other routing protocol we need to mention here, and that's Border Gateway Protocol, or BGP. This routing protocol is used on the public internet in order to move
Today is
routes
not a good day for no one.
businesses and internet service providers. BGP is kind of nifty because it's more like a scripting language with lots of parameters that we can configure, and those parameters allow us to implement contracts that two different internet service providers might agree to in order to figure out who pays for what traffic as it's moving across the internet. Now, we categorize these routing protocols into different categories. The only time I've ever really used these categories is on an exam. I have really never talked about these categories when I am working with other engineers. I don't say, hey, we should use a distance vector routing protocol here. I've never said that ever. But I have taken many exams where it asks me which of these routing protocols are distance vector protocols. So RIP and EIGRP are distance vector protocols. OSPF is a link state routing protocol. It pays attention to the different links and keeps a map of all the links so it can provide the best path through that network. And BGP is kind of a hybrid. It makes use of lots of different parameters so that engineers and businesses can figure out the best path to allow two internet service providers or two businesses or a business and an ISP the best path to move traffic through a network. These top three are called interior gateway protocols. In fact, EIGRP has interior gateway protocol written right in it. These are meant for inside of a business. And then BGP is an exterior gateway protocol, meaning it's used to route traffic between different businesses or different ISPs. Each of these routing protocols is given an administrative distance, and that way if we have more than one routing protocol running on our system, our routers know which route to use in the routing table. The higher the number here, the lower the priority of routing protocol. So RIP is given the lowest priority, BGP is given the highest priority, and EIGRP and OSPF sit right in the middle. So this is the route priority. It determines which route is the good one to add to the routing table. It's a lot of information we covered about how to route messages across the network. Let's go do a demonstration now and use traceroute to map the path of a packet as it goes between my workstation and Google. So here I am on my Windows 10 workstation once again. I'm going to open up my command prompt, and at my command prompt now, I can send a ping message to 8.8.8.8. Now that is Google's DNS server. It's an easy address to remember, and the reason that I like to use it a lot because it's easy to remember and it's a quick way for me to validate whether my internet is working correctly or not. If I can ping 8888, that means yes, my internet is up. If I'm having problems, it means that it's not because of my internet connection, most likely. If I can't ping 8888, that means that something is wrong with my internet and I should do no more work on trying to reach devices on the internet until I solve my problem. So we'll send a message here to 8888, see if I can reach it. I can. So let's do a trace route to that. So on Windows, the command for traceroute is tracer-t. And then what I do is I put in the destination. And I want to add a switch to this called -D, and that switch in the command is going to stop resolving the IP addresses to host names. Sometimes I can just add an extended amount of time into this process, because what I'm going to be doing is sending a message to every single router along the way and asking it to tell me some information about it. We're going to add the -D switch onto it and hit enter. Maybe it's not written correctly. Let's try tracer T-D8.8.8.8. There we go. I just had the D in the wrong spot. So it has to come before the address. So once we set it off, it's going to start working, and it's going to tell me information about what's happening. So what we're looking at here is we're seeing that there are 12 routers or 12 devices between myself and 8888 here at the bottom. And what I'm looking at is in each one of these, it gives me 3 times. This says less than a millisecond, less than a millisecond, less than a millisecond. That's because every single message that I send out a trace route, I send actually 3 of them. So and it's telling me the amount of time it took to get a response back from that router. So here I sent 3 messages, and it took each a millisecond each, or less than a millisecond each, to get back. The first router that I hit has an IP address of 192.168.142.2. It's on my local private network. Same thing with the second one, 10.128.50.1. That's also on my local private network. That is my router that I have configured up on my network. 192.168.1.254, that is actually my fiber optic modem. It should have a public IP address. I'm not sure why it doesn't here. It still has a private IP address. But then we go to the next message here, 162.199.184.1. This is going to be my AT&T's public IP address. It's on their routers. And then we can see it goes through numerous public routers before we finally reach 8888 over at Google. And to get to Google, it took 6 milliseconds for each one of those messages to reach Google and come back to us. That's pretty quick. So this is how traceroute works. If we do traceroute without that -D switch, it's going to take a little bit longer, but we might get more information about each of the devices. It's going to take longer here because I don't actually have that IP address 192.168.142.2 in DNS so that I can reverse resolve it. Nor do I have 10.128.50.1, nor 192.168.1.254. But then the 162.199.184.1, that does have a URL associated with it with sbcglobal.net. That is AT&T. You can see some more AT&T routers there. Some of these simply won't resolve because they don't have an entry in DNS, and that's pretty normal. But you can see how much longer this process takes when we leave the DNS resolution turned on. So this is a fun utility to play around with. You can't break anything. You get to see some information about the internet. Sometimes the routers don't respond, so we don't always get responses back from the internet. And those will show up as stars in this list. That's okay. Don't worry about if you see stars in the list. It means that we just can't get to those routers. They don't want to tell us information about them. And just play around with it. Like I said, you're not going to cause any harm to anything. You're just going to be looking around the internet. It's kind of like surfing the web, but you're just doing it in the command line interface in a much nerdier way. Let's wrap up what we've talked about in this module. We did a brief review of the OSI model, saw that we were going to be examining the connection between the data link layer and frames and the network layer and packets. We introduced network layer communication with IP packets. We explained how ARP worked and saw how necessary address resolution protocol is to build frames correctly to get those packets to route from the workstation to a router and so on. We described the default gateway and saw how important that router is in our network. Then we described IP routing and took a look at different methods of constructing routing tables, and wrapped it all up by taking a look at traceroute and seeing how traceroute can show us all the different routers in between our workstation and whatever device we're trying to reach on the internet. I hope you found this really valuable. In data networking, this routing technology is some of the cooler stuff to get to work with. It's kind of like the plumbing of the internet. It's really what makes everything work and gets messages from one device to another. And understanding it gives you a leg up in almost every single technology that you'll work with in IT. Hi everybody, I'm Ross Bagurtis and welcome to this next module where we're going to talk about wireless networking. Now, our module goals are going to be first to talk about the basics of wireless and discuss the physical layer components of wireless, including wireless channels. Then we're going to move up to the data link layer of wireless and talk about the 802.11 protocols that allow us to communicate with wireless, as well as the technologies involved in each of the 802.11 protocols. Then we're going to talk about encrypting wireless and how we secure wireless networks to prevent people from snooping in on our data. And last, we'll wrap up and talk about cellular wireless options specifically used for data networks. So when we look at the OSI model and we talk about wireless networks, there are two components to it, just like we saw in other versions of Ethernet. We took a look at the physical layer components using copper cables and fiber optics, and then we took a look at how Ethernet operated at the data link layer. Well, here we're going to do the same thing. We're going to take a look at the physical layer components of wireless Ethernet, and then the data link layer components of wireless Ethernet. So let's check out the basic physics of wireless. This is the physical layer component of it. So we've seen this electromagnetic spectrum before when we talked about fiber optics and using lasers to light up those fiber optics. We saw that the infrared part of the spectrum is what we used here. The electromagnetic spectrum is made up of different wavelengths of photons traveling through space. Over on the far left, we have the very large wavelengths that includes AM and FM radio, TV, and then as we move closer to the visible light spectrum, we get radar, infrared, then visible light, and then as we move away from the visible light spectrum in the other direction, the wavelengths get smaller and smaller and smaller. And these wavelengths then can get to the point where they can actually be dangerous to living creatures because the wavelengths are actually smaller than atoms, and they can actually knock apart atoms as those waves, like gamma rays, hit our bodies, and it can cause things like cancer. So the electromagnetic spectrum here is consisted of basically waves of photons, which is a little bit messy way to say that. There's a lot of physics involved in this. We're not going to go too deep into that though, but we do need to understand what a wavelength is. So a wavelength is nothing more than in an electromagnetic wave, or any wave for that matter, we're measuring the distance between the peak of one wave and the peak of the next wave in the series. So the wavelength is that distance that is directly related to frequency. Frequency is measured in hertz, or cycles per second. What we do here is we're measuring the peak of each wave as it passes across a fixed point. And that is going to get us how many cycles per second that wave is moving, or it's our frequency. The shorter the wavelength, the higher the frequency. So if we keep getting shorter and shorter wavelengths, we're going to have more waves hit that center line of my drawing here more often, which increases the frequency. So shorter wavelength, higher frequency. So when we use the electromagnetic spectrum, we need to select a component of it that we can make use of and transmit a signal and receive a signal. And to do that, we need something called a channel. And a channel is a range of frequencies we can use to transmit information. A single frequency of the electromagnetic spectrum is not enough to transmit data, because what we need to do is we need to modulate between a couple different frequencies in order to encode the data on the signal or on that electromagnetic wave. So a channel is a range of frequencies we use to transmit information. When we're talking about wireless communication, the wireless communication that we're looking at here falls in this yellow bar here that I've drawn on the electromagnetic spectrum. And what we do is we select a range of frequencies there and divide it up into channels. So here is the 2.4 gigahertz Wi-Fi spectrum. 2.4 gigahertz is the frequency that we're using, and it's a frequency range between 2.4 gigahertz and 2.499 gigahertz. And we divide that up into numerous channels, but in order to make use of it for 802.11 wireless, we need a 22 megahertz channel in order to accomplish our goal of transmitting data. That 22 megahertz channel then composes itself of multiple individual channels. So each of these channels is about 5 megahertz apart. So when we're using wireless in the 2.4 gigahertz Wi-Fi spectrum, we can only use 3 different channels of the 13 or 14 channels, depending upon which country you're in, available to us. In this case, we use channel 1, 6, and 11, and those are the 3 channels we can use with 2.4 gigahertz wireless. Now, additionally, we have the 5 gigahertz wireless spectrum. That spectrum ranges from 5.170 gigahertz all the way up to 5.835 gigahertz. Now, these channels are 20 megahertz apart. We have 36, 40, 44, 48, and so on that we can use here. However, the channels in the middle, channels 52 through 140 here, these require something special. If we are going to use these channels in an 802.11 wireless Ethernet network, we have to use something called DFS, or Dynamic Frequency Selection. And the reason for this is these channels are also used by the military to do certain types of transactions, whatever those transactions might be. The military can use these for radar and other things. And if we have an enterprise network environment and we're near an area where the military might use these, our equipment needs to detect that some external entity is using these channels, and if they're using the channels, we need to automatically switch to one that isn't one of these channels. And this is a regulatory impact of using 5.0 gigahertz Wi-Fi spectrum here. In our home networks, you typically will not see the 5 gigahertz Wi-Fi spectrum use these at all, right? It only is going to use 36, 40, 44, 48, and then 149, 153, 157, and 161. So only 8 channels available in our home networks. However, in enterprise networks, we can make use of these additional wireless channels for 5 gigahertz because the systems we set up are capable of detecting the use of these channels and automatically switching to something different. So then for the physical layer of 802.11 wireless Ethernet, we have these 2 different spectrums of electromagnetic signals we can choose from in order to send and receive our data. So let's talk about wireless Ethernet protocols now, the 802.11 protocol suite. This is the data link layer components of wireless Ethernet. So let's talk about a history of this. Now, all these 802.11 protocols are part of the IEEE suite of protocols for wireless Ethernet. If you remember, I've talked about 802.something quite a bit. 802.something is referring to Ethernet. So remember when we talked about trunk links, it was 802.1q. That was an Ethernet protocol specifically related to trunk links. 802.11 are the protocols related to wireless Ethernet. To start off, in 1997, that's when 802.11 was first specified as a wireless Ethernet protocol. This was a very early version. It was specific for enterprise business markets. There was no wireless encryption involved. It was very expensive and had a very limited use. By 1999, we solidified wireless Ethernet a little bit more into two markets now. The home market with 802.11b, that's the consumer market, and then the enterprise business market with 802.11a. We're going to talk about the differences between these two protocols in just a bit, but the idea here was that these protocols were separated out so that industry could make use of one of them and consumer market would make use of a different one. The consumer market version was quickly found out to be too slow, so they enhanced it in 2003 with 802.11g, which gave it a little bit faster communication, a little bit more reliable system. Then by 2009, 802.11n was available. And 802.11n kind of converged the enterprise business market with the home network. It was still two systems. However, the protocol itself was used in both the consumer devices and the enterprise business devices. Now, if you don't know, when I say enterprise, what I mean there is a big business, something that has 1,000 users or 10,000 users or more in their network. So it's a very large business, and the data networks that are needed for that are a lot more sophisticated than your home network. Now, by 2009, almost every laptop and wireless device that you purchased had Wi-Fi built into it already. 2003, that started to happen, but before 2003, typically you had to buy a separate wireless card for your devices in order to make them work correctly. So by 2009, it made sense that a laptop that you used at work would need to support both the business wireless that's set up as well as the home wireless that's set up in order to have that be portable. And by 2009, smartphones were becoming very, very, very popular. That protocol was built into all the smartphones. As time passed, 2013 came around, we came out with 802.11ac, and then in 2018, we enhanced it again with Wi-Fi 6 with 802.11.ax. Let's go take a look at each one of these protocols individually now. Start with 802.11a. 802.11a used the 5.0 gigahertz spectrum only. Could transfer data up to 54 megabits per second, and it was initially for enterprise use only, like I said before. You did not typically have 802.11a in your home networks. You'd have to use 802.11b in your home networks. Then 802.11b here this is a 2.4 gigahertz spectrum only. It could transfer data up to 11 megabits per second, and it was initially for SOHO use only. SOHO is small office, home office use. 802.11g was an enhancement to 802.11b, and again used only the 2.4 gigahertz spectrum. It could transfer data up to 54 megabits per second, which is much faster. It could compete with 802.11a now, and it could be used in both enterprise and small office, home office, although typically we were still seeing enterprises using 802.11a. At this point, if you had a laptop with a built-in wireless card that was supporting 802.11g, you could use it both at work and at home. 802.11n then was a convergence of protocols for business and home use, and it could make use of both 2.4 and the 5.0 gigahertz spectrum. As wireless became more prolific, that 2.4 gigahertz spectrum became very heavily used, and if your neighbors were using it and you were using it, you could oftentimes get overlap of channels, and it made it more difficult to communicate at higher speeds. 802.11n offered us an opportunity to use both 2.4 and 5 gigahertz in order to increase our throughput on our wireless links. And we could transfer data at up to 300 megabits per second. So we're moving up to do faster and faster wireless transmission. To accomplish this, it uses something called MIMO, or multiple input, multiple output. And what MIMO is So it really just means we have multiple antennas here that we're using, and we can send signals on one antenna and have it received by our wireless access point. We could send data on a separate antenna and have it received by our wireless access point. We could also communicate simultaneously with both antennas, and that would increase the amount of data we could transfer to our wireless access points. 802.11ac now, that made use of the 5 gigahertz spectrum only. So we're moving away from the 2.4 gigahertz spectrum with 802.11ac. This could transfer data up to 1.3 gigabits per second, which is now a similar speed that we can get by having a wired connection. Now, with wireless, though, the throughput that we get is directly dependent upon lots of circumstances, including how far away from the access point we are, what is in the way between us and the access point. Are there walls? Are there trees? Is there water around? Is the building made of metal? Things like this. So the speed is directly related to our location and the physics around there. 802.11ac can make use of multi-user MIMO and beamforming. Now, what multi-user MIMO is it means that we can allow more than one wireless client with multiple antennas the ability to use the same access point with multiple antennas at the same time. MIMO initially only worked with one user at a time. Multi-user MIMO allows for multiple users to do this at the same time. In addition, beamforming became a thing, and beamforming is a really nifty implementation of a wireless technology that allows us to direct a signal right at the client. So we can use multiple antennas to triangulate and use some algorithms to figure out where in space the wireless client is, and then we can beam the signal directly to that client, and that allows us to have a very directed broadcast of the electromagnetic signal that allows us to send more data faster to that device. 802.11ax, this is our modern standard here. This is Wi-Fi 6. This can use 2.4 gigahertz, 5 gigahertz, plus the ISM bands. That is the industrial, scientific, and medical bands, which were typically reserved for research purposes. And here with 802.11ax, we have an opportunity to use more channels in order to get more throughput to our devices. This can make use of MIMO and multi-user MIMO and beamforming as well as something called OFDMA. OFDMA stands for Orthogonal Frequency Division Multiple Access. This really is a pretty sophisticated topic to understand. When we're talking about electromagnetic signals, there's multiple accesses that we can send the data on, and OFDMA makes use of sending as much data, packing as much information as we can onto one wireless signal as possible. So it allows us to really increase our reliability and our throughput to our devices using OFDMA. Talk about wireless Ethernet operation now and some of the terminology we need to understand in order to learn how wireless networks actually work. So in our home or small business Wi-Fi network, a SOHO network, we're typically going to have just one access point or maybe two access points working as a pair with each other. And that access point is going to send out a signal to wireless clients in our home. Those wireless clients might be a laptop, it might be a smartphone or a tablet, or this light bulb here, I'm indicating that's an IoT device or Internet of Things device, like a smart light bulb. Could be a smart outlet or some toy or other things in our network. So the access point is the central hub. That's the device that's sending out the signal and it's receiving the signal. Our wireless clients, like I said, this could be laptops, smartphones, tablets. And this is all using something called a basic service set, or BSS. And that is the idea that this access point is sitting there individually serving up clients in our home or small office. The BSS ID, the basic service set ID here, is the MAC address of our wireless access point. So because we're using Ethernet here, Our access point is going to have a MAC address associated with it, and our clients are going to send their traffic to that MAC address. And the SSID is the Service Set Identifier, or the Service Set ID. The SSID, that's the name of our wireless network. So when you visit your friend's house and they say, hey, what's your Wi-Fi network? You're telling them the name of the SSID here. In order to make this work, our wireless access point is almost always using something called an omnidirectional antenna, meaning that that antenna sends out a signal in virtually every direction uniformly. It can't do that perfectly. However, the idea of the omnidirectional antenna is that we send out the signal as uniformly as we possibly can based on the limitations of physics involved with using electromagnetic signals. A contrast to that is a point-to-point wireless network, which is going to use a directional antenna. Directional antennas just really aim the signal at a very small range, and that way we can get a very powerful signal to go a pretty big distance. That way, if we have two buildings that are a couple miles apart or a couple kilometers apart, what we can do is we can connect those two buildings together with a wireless network instead of installing fiber optics between these buildings or purchasing some service from an ISP. And the idea here is that the antennas will send out a signal to each other, and they'll receive that and be able to do communication between these two buildings. One of the problems, though, is that with wireless networks, if you put something in the middle between it, you're going to interrupt the wireless signal and it's not going to work quite as well. I worked for an organization once and we had this exact setup where we had two buildings with directional antennas on the roof, and we had them connected together, but every spring the tree would get its leaves again and it would grow a little bit taller and it would interrupt that wireless signal, and the users in one of the buildings would always complain that they would lose their network access. So we ended up having to put fiber optic to the building eventually. So when we're using wireless networks to connect buildings together like this, to do WAN connections between buildings, we have to pay attention to make sure that nobody's going to construct another building or there's not trees growing there. Now, the main solution for this is something like a Yagi directional antenna. It looks like this image here. That is a directional antenna we can use to do point-to-point networks for wireless. Another way you can do this at home, if you want to build a home wireless network with a point-to-point network, you can find specifications to build something called a cantenna. You can actually use a Pringles can to make a wireless network, a wireless point-to-point network to send signals between each other. You can do this for very inexpensively, just a few dollars to make this cantenna network. So if you have a larger property and you're trying to get wireless networks between them, you might want to look at something like this Pringles cantenna out on the internet and see if you can build it to make a point-to-point wireless network. Wireless signal strength and quality are very important when we're talking about wireless networks. Now, we measure our signal strength in decibels, which is labeled dB. So our signal strength is measured in decibels, and then we have something called a signal-to-noise ratio. And we really want the highest signal-to-noise ratio we can get. We want a lot of signal and not a lot of noise. And what I mean by this here is that if we have a wireless network, especially a 2.4 gigahertz wireless network, and this access point is sending out its signal, that signal can be interfered with by other devices, especially microwaves. A microwave also operates at 2.4 gigahertz. And the reason is that at 2.4 gigahertz, that will resonate with a water molecule and actually make a water molecule spin around. And when we put food in the microwave, there's water in the food, and we can spin those water molecules around, which then rub up against the other stuff in the food, and that heats up the food. It creates friction inside the food. So the microwave oven is actually cooking the food from inside the food. The heat is generated from inside. When we turn on that microwave, though, it sends out a massive, super loud, uncontrolled 2.4 gigahertz wireless signal, which ends up as being noise. So when that happens here, you can kind of see my signal disappearing and reappearing. And that would mean that the signal to noise ratio is very low, meaning there's lots of noise and not a lot of signal. which means that we can't actually use that signal then to send and receive traffic. So sometimes if you're standing near a microwave when it's on, you may lose your wireless network capabilities. Now, another thing we can do here is something called wireless channel bonding. And remember in the beginning, I said in our 2.4 gigahertz wireless spectrum, we had 22 megahertz wide channels, and we could use channels 1, 6, and 11. Well, one of the things we might do here is take channels 1 and 6 at 22 megahertz each and combine them together into a 44 megahertz channel. And that would allow us to send on channel 1, we could send 54 megabits. On channel 6, we could send 54 megabits. And when we combine them together, we can actually get a combined 108 megabits of throughput between our two devices. So wireless channel bonding allows us to take multiple channels, bond them together to get enhanced throughput between our devices. So let's take a look at topologies and management of wireless networks. So there's several different wireless topologies we can set up. We can set up an ad hoc wireless network. This is used very rarely. We can set up a mesh network. Those can be used especially in outdoor environments. We can use wireless mesh networks, and we can have infrastructure wireless networks. So a mesh wireless network is something that we would use when maybe we're setting up Wi-Fi in the city, and we're setting it up on the city streets for an outdoor use. We can put access points on telephone poles and city street lights. The access points themselves won't need a separate network connection going to them, because what we'll do is we'll actually use a wireless mesh, meaning that those wireless access points on the telephone pole, they can connect to wireless clients walking along the street, and they can also communicate with other wireless access points to provide them network access. The infrastructure mode is what we're going to use inside of our home networks, inside of our business networks. Ad hoc wireless networks use something called the Independent Basic Service Set. They typically are small Wi-Fi networks. They're used for sharing files and whatnot, used for toys or other electronic gadgets. I have a GoPro camera, and I can connect to it via an ad hoc wireless network in order to transfer the video files off of the GoPro onto my laptop. Sometimes toys will set up mini Wi-Fi networks as well, so that you can communicate with them or set them up or control them. Infrastructure wireless networks here are going to use something called an extended service set. So remember that home network that I talked about? That home network I talked about used a basic service set, and it was just a single access point with a single infrastructure on it so that we could connect our wireless devices to that single AP. In an enterprise network, we're going to use something called an extended service set, an ESS. And that is used in enterprise Wi-Fi networks. And here we use that because typically in Wi-Fi networks, in big businesses or bigger businesses, we're going to have more than one access point that we need to configure. We don't want to have a separate SSID for every single access point. So with ESS, it allows us to have many, many, many access points, all operating on different channels, all using the same SSID. So that way I can roam around to different access points and never lose my network connection. In order to configure all these access points, we use something called a wireless LAN controller. So with that, as an administrator, I would go onto the wireless LAN controller, create some profiles that I would push out the config to multiple access points. This is relative to the way you would do it at home. At home, you would connect directly to your access point, typically, and configure that access point individually. And we used to do this in wireless networks for business. However, there became so many access points, this became very, very difficult to do. So we went to this controller-based model where we can create profiles that we can send out to access points, and it allows us to give different services to different areas of our network. We also want to be able to roam around. So here in this office building, this is a floor plan of an office. Maybe we have a warehouse over there on the left, and there's some people moving around there constantly. And then inside the rest of the office, maybe we have, users that are going to move from their office and they might move into a conference room at some point. So all this means that we have to provide enough wireless access to our devices so that as these users roam around, they have continuous access to a wireless network. So we might do something like a wireless site survey to determine where our access points need to be placed in order to provide the coverage so that we can roam around our office building or our warehouse or wherever we're at and have continuous coverage of Wi-Fi to keep our users happy. So let's take a look at topologies and management of wireless networks. So there's several different wireless topologies we can set up. We can set up an ad hoc wireless network. Let's talk about wireless encryption next. The need for wireless encryption comes from this. Wireless is not like a wire. Of course it's not. If I plug my device into a wire, the only two devices that can hear that traffic is the device that's sending the traffic and the device that I'm sending it to. So that might be a switch, and the switch might be connected to a router, but I would have to be a device on that network to somehow receive the traffic. With wireless, I don't have to be connected to the network. I don't even have to be inside of the house or the business that's sending out the wireless signal. I can do something called war driving, which is driving around with a laptop searching for wireless networks that I can break into. And if I can break into the wireless network and get connected to it, then I can see a lot of the traffic that's being sent and received on that wireless network. I can capture it and examine it and see if I can gather any useful or sensitive information. War driving is not a legal activity. However, it can be done and it's difficult to detect. And I'm certainly not encouraging you to do that. I'm just saying this exists and it's the reason why we need to encrypt our wireless networks. So early encryption, especially on 802.11b, we use something called WEP, Wired Equivalency Protocol. And the name is kind of a joke now. The idea was that they were going to make this wireless encryption so that it would be the same as being connected to a wired network. But by 2002 or so, utilities existed to be able to crack the password used for WEP within seconds. So you could capture the wireless password or the pre-shared key here using WEP. You could capture it in a matter of seconds and break into somebody's network. So we needed to abandon WEP very quickly, which is where we came out with WPA, or Wi-Fi Protected Access. And this used one of two types of encryption in order to accomplish the goal. One was TKIP, which is Temporal Key Integrity Protocol, and that was basically an extension of WEP. So as we made the migration, we had to write software and update our hardware in order to accomplish the new encryption standard. But in order to make it a little bit backward compatible, we implemented TKIP, which is very similar to WEP and actually is kind of easy to decrypt our key used to encrypt our data. So that's why we would prefer to use AES, or the Advanced Encryption Standard Protocol, for our encryption. So WPA supported both of these, TKIP as a backward compatibility type thing, and AES as our more sophisticated and preferred encryption standard. Over time, though, WPA also was easy to crack the way it was implemented, so we implemented WPA2. Now, WPA2 is Wi-Fi Protected Access 2, and it also does both TKIP and AES, but has additional mechanisms built into the protocol to make it much more difficult to crack the password used in order to encrypt our data. AES and WPA, we don't want to use those on any of our networks anymore unless we absolutely have to. Sometimes in medical environments or manufacturing environments, the equipment we're using was either made to survive an extended period of time, 10 years or more, or it was certified by some body like the FDA in the United States that allows that medical gear to be used in a hospital. And when they do that, sometimes they have to certify it with very specific hardware that may not be capable of advanced encryption options. So in those cases, we create firewalled networks in order to protect that equipment as much as we can. When we have the opportunity, we want to use a minimum of WPA2 encryption. And when we're talking about that, we definitely don't want to use our TKIP option anymore, unless, again, we absolutely have to. We want WPA2 using AES encryption. There are two flavors here of WPA2 that we can use. One is personal. This is what we would use at home with the pre-shared key. When somebody comes into your home, they say, hey, what's your wireless network? And you tell them, and then they say, okay, I need the passcode. That's the pre-shared key you're giving them, the PSK, right? And you configure that on your wireless equipment. The second option here is enterprise version of WPA2. And with enterprise, we're using a protocol called 802.1x. Remember, 802 is the Ethernet stuff protocols. 802.1x is an authentication protocol at layer 2 that we can use to authenticate a user or some other method onto our network. This is going to use in wireless something called EAP-TLS in order to achieve that authentication. And with that, we can use a username and password. We can also use something called a certificate. In a certificate, we can generate a very specific certificate for a specific device like a laptop or a smartphone. We can install that certificate on the device, and then when we try to connect to our wireless network using WPA2 in enterprise mode, we can send that certificate and say, hey, here's my certificate, I'm authentic, authenticate me. And the wireless network will then say, oh yeah, this is legitimate, you're authenticated. Or if the certificate isn't valid, maybe it expired, or maybe it was removed from the allowed certificates from the 802.1x system, then it would say reject that connection, not allow the wireless client to connect. So in enterprise businesses is very useful because then we're not giving everyone the same pre-shared key. We can add or remove devices from the network or add or remove users from the network as we need to. If a user gets fired, we want to invalidate their username and password and prevent them from getting on the wireless network. And if we had a pre-shared key, we'd have to change that pre-shared key and give it to everybody again, and that would make a messy situation. WPA3 is the latest version of WPA, and that really is just using AES encryption, and it's using just more bits of AES encryption. So it's slightly more secure, slightly more difficult to attack. Let's wrap up our conversation about wireless here by talking about cellular wireless. Now, cellular wireless came in many different flavors over the years, and we started off specifically when we talk about data networks and cellular wireless. It's evolved quite a bit over the last 20 years. The original versions of cellular all used analog-based connections. They were a poor connection. They didn't do a great job with even the voice traffic. And they didn't have a huge range. Later on, we went to digital cellular communication, and that allowed us a lot more options, although our data capabilities on that were very, very, very limited. That was up until we came out with this TDMA, or Time Division Multiple Access. Now, TDMA was the type of cellular technology that allowed us to transfer data, but it allowed it at a very slow speed. This was the technology available when the iPhone first came out in 2007. Then we came out with GSM, the Global System for Mobile Communications, and this standard was used generally around the world. In the United States, it was only used on 1 or 2 carriers, and GSM allowed for a faster speed communications between devices, and a competing model to this was CDMA, or Code Division Multiple Access. So GSM and CDMA were used by different carriers. So GSM was used by AT&T and T-Mobile in the United States. CDMA was used by a lot of small carriers in the US and Verizon Wireless. CDMA was used a lot more in the United States than it was used in the rest of the world. GSM was the primary technology there. Then we moved on to LTE, or long-term evolution. LTE could make use of either CDMA type technology or GSM type technology to achieve higher data rates. LTE is still very popular around the world, and we're slowly moving on from it though. So TDMA, that was a 2G wireless cellular network. GSM was considered 3G or third generation. CDMA also 3G. LTE is our 4G network. And then now we're using LTE, the long-term evolution, to also move on to 5G networks. And 5G networks generally are still using the same technology as the LTE stuff. We're just changing how the infrastructure operates on the back end to achieve a much lower latency, high-speed network. We are making some use of some new frequencies in 5G networks. However, those are typically for big cities versus other applications of this. Let's wrap up all the things we've talked about with wireless networks here. We talked about the basics of wireless and discussed the physics or the physical layer of wireless and how we make use of wireless channels in the electromagnetic spectrum. We then moved on and talked about the data link layer component of this with 802.11 protocols and technologies like multiple input, multiple output, OFDMA, among other things. We talked about encrypting wireless, how we want to use WPA2 or WPA3 to encrypt our wireless networks. And we wrapped it all up by talking about the different cellular technologies we use to transfer data. I hope this gives you a great introduction to wireless networks, specifically wireless Ethernet and those 802.11 protocols. Those are going to be very useful. All those terms are going to be very useful for you in your career in IT and in data networking. Can hear that traffic is the device that's sending the traffic and the device that I'm sending it to. So that might be a switch, and the switch might be connected to a router, but I would have to be a device on that network to somehow receive the traffic. With wireless, I don't have to be connected to the network. I don't even have to be inside of the house or the business that's sending out the wireless signal. I can do something called war driving, which is driving around with a laptop searching for wireless networks that I can break into. And if I can break into the wireless network and get connected to it, then I can see a lot of the traffic that's being sent and received on that wireless network. I can capture it and examine it and see if I can gather any useful or sensitive information. War driving is not a legal activity. However, it can be done and it's difficult to detect. And I'm certainly not encouraging you to do that. I'm just saying this exists, and it's the reason why we need to encrypt our wireless networks. So early encryption, especially on 802.11b, we use something called WEP, Wired Equivalency Protocol. And the name is kind of a joke now. The idea was that they were going to make this wireless encryption so that it would be the same as being connected to a wired network. But by 2002 or so, utilities existed to be able to crack the password used for WEP within seconds. So you could capture the wireless password or the pre-shared key here using WEP. You could capture it in a matter of seconds and break into somebody's network. So we needed to abandon WEP very quickly, which is where we came out with WPA, or Wi-Fi Protected Access. And this used one of two types of encryption in order to accomplish the goal. One was TKIP, which is Temporal Key Integrity Protocol, and that was basically an extension of WEP. So as we made the migration, we had to write software and update our hardware in order to accomplish the new encryption standard. But in order to make it a little bit backward compatible, we implemented TKIP, which is very similar to WEP and actually is kind of easy to decrypt our key used to encrypt our data. So that's why we would prefer to use AES, or the Advanced Encryption Standard Protocol, for our encryption. So WPA supported both of these, TKIP as a backward compatibility type thing, and AES as our more sophisticated and preferred encryption standard. Over time, though, WPA also was easy to crack the way it was implemented, so we implemented WPA2. Now, WPA2 is Wi-Fi Protected Access 2, and it also does both TKIP and AES, but has additional mechanisms built into the protocol to make it much more difficult to crack the password used in order to encrypt our data. AES and WPA, we don't want to use those on any of our networks anymore unless we absolutely have to. Sometimes in medical environments or manufacturing environments, the equipment we're using was either made to survive an extended period of time, 10 years or more, or it was certified by some body like the FDA in the United States that allows that medical gear to be used in a hospital. And when they do that, sometimes they have to certify it with very specific hardware that may not be capable of advanced encryption options. So in those cases, we create firewalled networks in order to protect that equipment as much as we can. When we have the opportunity, we want to use a minimum of WPA2 encryption. And when we're talking about that, we definitely don't want to use our TKIP option anymore unless, again, we absolutely have to. We want WPA2 using AES encryption. There are two flavors here of WPA2 that we can use. One is personal. This is what we would use at home with the pre-shared key. When somebody comes into your home, they say, hey, what's your wireless network? And you tell them, and then they say, okay, I need the passcode. That's the pre-shared key you're giving them, the PSK, right? And you configure that on your wireless equipment. The second option here is enterprise version of WPA2. And with enterprise, we're using a protocol called 802.1x. Remember, 802 is the Ethernet stuff protocols. 802.1x is an authentication protocol at layer 2 that we can use to authenticate a user or some other method onto our network. This is going to use in wireless something called EAP-TLS in order to achieve that authentication. And with that, we can use a username and password. We can also use something called a certificate. In a certificate, we can generate a very specific certificate for a specific device like a laptop or a smartphone. We can install that certificate on the device, and then when we try to connect to our wireless network using WPA2 in enterprise mode, we can send that certificate and say, hey, here's my certificate, I'm authentic, authenticate me. And the wireless network will then say, oh yeah, this is legitimate, you're authenticated. Or if the certificate isn't valid, maybe it expired, or maybe it was removed from the allowed certificates from the 802.1x system, then it would say reject that connection, not allow the wireless client to connect. So in enterprise businesses is very useful because then we're not giving everyone the same pre-shared key. We can add or remove devices from the network or add or remove users from the network as we need to. If a user gets fired, we want to invalidate their username and password and prevent them from getting on the wireless network. And if we had a pre-shared key, we'd have to change that pre-shared key and give it to everybody again, and that would make a messy situation. WPA3 is the latest version of WPA, and that really is just using AES encryption, and it's using just more bits of AES encryption. So it's slightly more secure, slightly more difficult to attack. Let's wrap up our conversation about wireless here by talking about cellular wireless. Now, cellular wireless came in many different flavors over the years, and we started off specifically when we talk about data networks and cellular wireless. It's evolved quite a bit over the last 20 years. The original versions of cellular all used analog-based connections. They were a poor connection. They didn't do a great job with even the voice traffic, and they didn't have a huge range. Later on, we went to digital cellular communication, and that allowed us a lot more options, although our data capabilities on that were very, very, very limited. That was up until we came out with this TDMA, or Time Division Multiple Access. Now, TDMA was the type of cellular technology that allowed us to transfer data, but it allowed it at a very slow speed. This was the technology available when the iPhone first came out in 2007. Then we came out with GSM, the Global System for Mobile Communications, and this standard was used generally around the world. In the United States, it was only used on 1 or 2 carriers, and GSM allowed for faster speed communications between devices, and a competing model to this was CDMA, or Code Division Multiple Access. So GSM and CDMA were used by different carriers. So GSM was used by AT&T and T-Mobile in the United States. CDMA was used by a lot of small carriers in the US and Verizon Wireless. CDMA was used a lot more in the United States than it was used in the rest of the world. GSM was the primary technology there. Then we moved on to LTE, or long-term evolution. LTE could make use of either CDMA type technology or GSM type technology to achieve higher data rates. LTE is still very popular around the world, and we're slowly moving on from it though. So TDMA, that was a 2G wireless cellular network. GSM was considered 3G, or third generation. CDMA also 3G. LTE is our 4G network. And then now we're using LTE, the long-term evolution, to also move on to 5G networks. And 5G networks generally are still using the same technology as the LTE stuff. We're just changing how the infrastructure operates on the back end to achieve a much lower latency, high-speed network. We are making some use of some new frequencies in 5G networks. However, those are typically for big cities versus other applications of this. Wrap up all the things we've talked about with wireless networks here. We talked about the basics of wireless and discussed the physics, or the physical layer of wireless, and how we make use of wireless channels in the electromagnetic spectrum. We then moved on and talked about the data link layer component of this with 802.11 protocols and technologies like multiple input, multiple output, OFDMA, among other things. We talked about encrypting wireless, how we want to use WPA2 or WPA3 to encrypt our wireless networks. And we wrapped it all up by talking about the different cellular technologies we use to transfer data. I hope this gives you a great introduction to wireless networks, specifically wireless Ethernet and those 802.11 protocols. Those are going to be very useful. All those terms are going to be very useful for you in your career in IT and in data networking. Hi everybody, I'm Ross Pagurtis. Welcome to this next module, Layer 2 Devices and Services. We're going to start by talking about modems. Then we're going to talk about traffic shaping and see how we can give certain traffic priority on our network. And last, we're going to look at neighbor discovery protocols and see how those are relevant in our networks. Before we get into all that, I did title this module Layer 2 Devices and Services, which means that everything I'm talking about in this module is going to be relevant directly to the data link layer. These are all Layer 2 protocols that we're working with, Layer 2 stuff. Let's start with modems. Now, modem itself stands for modulator, demodulator, and the original modems that we would use were actually a device that we would put on our telephone line and hook it into our computer in order to get some type of networked service. Initially, that was to a bulletin board service or a BBS, which allowed us a text-based menu to transfer files and maybe do some chatting, maybe play some text-based games and whatnot. And all that modem did was it took a signal that the computer could understand and it converted it into sounds and screeches and whatnot that it was able to send that data connection over the phone line itself. It was a very slow operation. However, the modem eventually evolved into providing us internet connectivity in our homes. So it's very likely that you have a device like this in your home if you have some type of wired internet service in your home or your business. This device here provides wireless access. It also provides some wired Ethernet access, but then it also has an interface to connect back to the internet service provider. And this device is converting a signal that's Ethernet that our computers and our phones can understand, and it's converting it into a signal that the internet service provider can understand. So here is a cable modem that I have an image of here. And the cable modem, what it's doing is it's taking a protocol, a layer 2 protocol called DOCSIS, which is Data over Cable Service Interface Specification. So it's the protocol that's used to transfer data over a cable TV wire, over that coax cable. So DOCSIS is the connection that goes to the cable company. Ethernet is what we're going to use in our internal home network. So this device, this cable modem, is converting DOCSIS to Ethernet for us. Another type of modem we can have is a fiber optic modem. Now this is more of a media converter than it is a modem, even though we'll likely refer to this as a modem. The fiber optic modem, the media converter here, what we're doing is we're taking fiber optic Ethernet connections and we're converting it into copper Ethernet connections. So this device that we get from our internet service provider has a fiber optic port that we plug the fiber optic into, and that connects back to the internet service provider, and it converts it into copper Ethernet, which we can plug our devices into, or plug a wireless access point into, or some other type of Ethernet connection. Now, these modems that we get from our internet service provider are usually a little bit more sophisticated than just being a layer 2 media converter. It often has other options on it like firewalls and whatnot to help protect our internal systems from the ugliness that exists on the internet. But the idea here generally is that this fiber optic modem from our internet service provider is just converting our fiber optic Ethernet into copper Ethernet. Another type of modem here is a DSL modem, or a digital subscriber line modem. These were very popular in the late 90s, early 2000s, before the cable infrastructure was completed, and certainly before we had any fiber optics into our homes. So the DSL modem is digital subscriber line. It runs over our telephone wires. So the telephone wires that are in our homes that give us land phone lines, if we still have a land phone line, we can use those land phone lines to provide internet service via DSL. Now, DSL used audio, but the audio is outside of the range of human hearing, and we were able to put specialized equipment in our central offices of the telephone companies, as well as use a DSL modem to provide higher speed internet access at like a megabit or 2 megabits per second. It was relatively slow for modern standards, which means that this is actually antiquated now. We don't use this very much anymore. However, maybe in rural environments or in areas of the world where we don't have access to fiber optics or high-speed wireless or cell infrastructure or cable modems, we might be using DSL infrastructure. The DSL modem here is typically converting the DSL signal, the digital subscriber line protocol that's used over the phone line to communicate to the internet service provider. It's converting that from DSL to Ethernet. That's what the purpose of this particular modem is. Next, let's talk about traffic shaping. Now, traffic shaping is very useful when we have some traffic that needs high priority and definitely needs to get across the network quickly versus traffic that can have a little bit more latency involved. It doesn't have to be prioritized at all. And the distinction here is a distinction between making a phone call using voice over IP, which uses the data network, versus streaming a video from YouTube. For streaming a video from YouTube, YouTube can slowly gather the video, slowly download the video, and it can cache it in our browser so that when we hit play, we get a nice continuous stream of video. We don't really have to worry about if there's latency on the network. A voice over IP call, though, that's happening real time and live, and if we drop a packet, we don't get that packet later. It just doesn't show up at all. So we miss part of the conversation. So let's take a look at how we can use traffic shaping to our advantage here. So let's say I have two networks here. Here's two clouds with some network in it, and those networks are sending some traffic. So as that traffic reaches the switch, by default, the switch is going to process the traffic in a first come, first serve basis. So latency involved, it doesn't have to be prioritized at all. And the distinction here is a distinction between making a phone call using voice over IP, which uses the data network, versus streaming a video from YouTube. For streaming a video from YouTube, YouTube can slowly gather the video, slowly download the video, and it can cache it in our browser so that when we hit play, we get a nice continuous stream of video. We don't really have to worry about if there's latency on the network. A voice over IP call, though, that's happening real time and live, and if we drop a packet, we don't get that packet later. It just doesn't show up at all. So we miss part of the conversation. So let's take a look at how we can use traffic shaping to our advantage here. So let's say I have two networks here. Here's two clouds with some network in it, and those networks are sending some traffic. So as that traffic reaches the switch, by default, the switch is going to process the traffic in a first come, first serve basis. So just like you're going to the grocery store and you get into one of the lines at the grocery store, it's first come, first serve. There's no priority based on your status or how many groceries you have or anything like that. You get into the line that's available, first come, first serve. Well, if we do that same demonstration, but we use voice over IP here, we're going to pay attention this time to the blue messages at the top, which are coming from the phone. So with first come, first serve here, we want the phone messages, those blue envelopes at the very top of that group of messages there that I've shown, we want those to flow in a nice stream. But if we process that first come, first serve, watch what happens. We have this huge delay before we get another message of our voice call onto that wire. So there's these delays as we're putting messages onto the wire and processing it through the switch. So when we have voice over IP traffic, we definitely don't want our traffic to be prioritized first come, first serve. We really want our voice over IP traffic to have definite priority and get onto the wire faster and more consistently. So if you think of the grocery store again, there are oftentimes in grocery stores a express lane. And the express lane is for people who have less than 10 or 15 items. They can go into the express lane so that we're not in the same lane of traffic where the person in front of me has two grocery carts full of food that needs to check out when I only have two things in my hand. That way I can go to the express lane and check out there. So here, if we introduce traffic shaping, now what we can do is we can take those voice over IP messages coming from our phone and we can give them a special cue. So I've drawn that purple line up there. That's my special cue. So now whenever I send a message onto the wire, every other message is my voice over IP message. And that way, as I'm talking on the phone, those messages coming out of my phone are very nicely, neatly spaced on the wire, and we can guarantee them priority when they are transferring over the wire. So it's a matter of how we prioritize this traffic. The way we can do that is we can either add a special code into our header information, or we can configure our switch to give priority to certain VLANs over other VLANs. So with traffic shaping, it's really a form of bandwidth management. We can do this in lots of different ways. For voice over IP calls, we want to give those messages priority. In the sense of other traffic shaping, though, we can do some bandwidth management where maybe we purchase a 50 megabit internet connection over a fiber optic cable from our internet service provider. Well, 50 megabits, there is no 50 megabit Ethernet. There's 100 megabit Ethernet, there's a gigabit Ethernet, there's 10 gigabit Ethernet, but no 50. So what we can do with that is we can actually do some bandwidth management similar to the way we do prioritization of traffic for voice over IP. So we can actually limit the amount of bandwidth allowed on a link. That's one method we can use here. We can implement quality of service, and that's really what we're doing with traffic shaping when we're talking about voice over IP calls or video calls or other types of services, maybe emergency services that require a high level of priority on the data network. Flow control is another way of implementing quality of service. It's something that we can implement on our switches. to allow for traffic to be sent efficiently and effectively. Next, let's talk about neighbor discovery, which is another layer 2 function on our network. So when we have a bunch of networked devices like routers and switches, sometimes even firewalls, it's very easy to get lost in the mess of cabling and connections. So here's a very simple network that I've drawn here. What neighbor discovery does is it sends out messages at layer 2, very simple messages, and it says, hey, I'm a router, I have these capabilities, and this is the port that I'm sending this message out on. And then the device that's listening for that message says, oh, great, thanks, I'm going to add that to my table, and it sends back the same kind of information to the other device. This only happens with neighboring devices. So not all the devices see all the traffic. That would make a mess of our network. The idea here is that we want to see who is directly connected to us. This is an outstanding tool for troubleshooting networks when we are uncertain what devices are connected, or maybe we have some unusual behavior happening. Maybe a cable did not get reconnected correctly. So what we can use is we can use these neighbor discovery protocols then to learn about our neighbors. And the idea here is that if we take a look at this router in the middle, that router is going to learn about its neighbors through a neighbor discovery protocol. Its neighbors are going to be the switch on the left and the right and the router on the bottom. So in the table on this router, we could look at that table by issuing a command, and it would say, hey, there's a switch attached to the left, there's a switch attached to the right, there's a router attached below you, and these are the capabilities of that device. If we take a look at the switch over on the upper left, that's going to learn about the router and the switch that are directly connected to it. If we look at the router on the bottom, that's only going to learn about the router on the top and no other devices. And if we take a look at the switch on the bottom right, that's only going to learn about the switch that's directly connected to it and no other devices. So when we're looking at neighbor discovery protocols here, there's two that we generally use. One is link layer discovery protocol. This is for devices that are not Cisco based. The other one is CDP, or Cisco Discovery Protocol. CDP is prevalent on all Cisco devices. It is typically enabled by default. So we're able to see the devices that are directly connected to each other. Now, I've actually seen non-Cisco devices even using CDP. It's a pretty simple protocol. It's so widely deployed. It's very useful in discovering what network devices are directly connected to ourselves. This makes, again, tremendous use when we're doing troubleshooting. It can introduce a layer of potential security issue, because if somebody attaches to our device that is not authorized, they can look at this information from our neighbor discovery and learn more about our network quickly. Most organizations value the troubleshooting capabilities of this over the potential security risks, though. So we're going to do a demonstration here. We're actually going to go look at Cisco Discovery Protocol so we can see how these devices show what is directly connected to them. Next, let's talk about neighbor discovery, which is another layer 2 function on our network. So when we have a bunch of networked devices like routers and switches, sometimes even firewalls, it's very easy to get lost in the mess of cabling and connections. So here's a very simple network that I've drawn here. What neighbor discovery does is it sends out messages at layer 2, very simple messages, and it says, hey, I'm a router, I have these capabilities, and this is the port that I'm sending this message out on. And then the device that's listening for that message says, oh, great, thanks, I'm going to add that to my table, and it sends back the same kind of information. So we're going to do a demonstration here. We're actually going to go look at Cisco Discovery Protocol so we can see how these devices show what is directly connected to them. I have a drawing of the network that I have set up here. My network that I'm going to show you has 3 different devices, actually 4 different devices here. We're going to connect into switch A, And then I'm going to issue the command show CDP neighbor. And that's going to show me my Cisco Discovery Protocol table, which has all the devices that are directly connected to it. And in that table, we should see switch B or SW_B. We should see a switch labeled S3560, and we should see a router labeled RTR_B. And additionally with this, we're going to see port numbers among other things. So let's go over to my workstation so we can take a look. Here I am on my Windows 10 workstation now. Let's open up my PuTTY so I can connect via the serial port of my workstation to the console port of my router, or actually my switch here. So I'll open up that. It's going to give me this command prompt window. We hit enter. It should ask me to log in here. There we go. So if I issue the command show CDP neighbor, that's show Cisco Discovery Protocol neighbor, and I hit enter here, it shows me information about these devices. So here is S3560, and it has .ros.local. That's the domain that I use with my switches. And it looks like that switch is connected to my switch A here via fast Ethernet 0/2. So if I look over at my switch and on port 2, I can see that there's a cable running to the switch labeled S3560. If I move over, it says capabilities here, RSI. It says that it's a router. It says that it's a switch. It says that it is also supporting IGMP, or Internet Group Management Protocol. Well, this is a switch, I said, connected. Why does it have routing capabilities? Well, it's a special kind of switch called a layer 3 switch, which can do most routing functions as well as most switching functions. The IGMP, that's another protocol that's beyond the scope of this particular course. We can look at the platform though, WSC3560. This is a Cisco 3560 switch, and on that switch we are connected to port fast Ethernet 0/3. So on the 3560, if I look at it, I'm connected to port 3 on that switch, is connected to port 2 on this switch. If we look at the next one down here, it says RTR_B. That is my router. And that's connected to fast Ethernet 0/8 on my switch. And it is a Cisco 1841 series router. And I'm plugged into fast Ethernet 0/1 on that router. And then here the last one, SW_B. I am plugged into port fast Ethernet 0/1 on my switch right here that I'm looking at. And it is plugged into fast Ethernet 0/2 on switch B. And that is a Cisco 2960 switch. And you can see here that supports S and I. That supports switching only. That is a layer 2 only switch. So on this layer 3 switch at the top here, just briefly to explain what's going on with that, that switch is generally going to do all kinds of switching stuff, but we have the option of enabling routing capabilities as well. So it's kind of a 2-in-1 device, and these are very common in data networks nowadays. We can do VLANs, and we can also do routing tables on that single device. Let's wrap up what we've talked about today. We took a look at modems and saw the difference between 3 types of modems: a cable modem, a fiber optic modem, a DSL modem. And we learned that they're really doing some type of media conversion from one layer 2 protocol to another layer 2 protocol. We looked at traffic shaping and saw how we can take voice over IP traffic and prioritize it on the network by giving it a special queue. And then last, we took a look at Neighbor Discovery Protocol. Neighbor Discovery Protocol allows us to see our directly connected network devices that we're using. I hope this was valuable to see some layer 2 devices. We're going to wrap up the course in the next module. We're going to take a look at other network devices that are important to network infrastructure. However, they didn't necessarily fit into the other categories. So we're going to wrap up the course by talking about the other types of devices we see on a network and their purpose. Hi everybody, I'm Ross Bagurtis, and welcome to this last module in our network infrastructure course. Here we're going to talk about other networked devices that we couldn't fit into the other parts of this course. So our goals this module, first we're going to take a look at load balancers and see what they do. We'll look at firewalls and see some different firewall options we have. We're going to talk a little bit about voice over IP, and then we'll talk about some other network devices that we may find on our network that need IT support. So first, let's start with load balancers. Now, a load balancer is going to operate typically between the network layer and the transport layer. We may have some application layer functions here as well. What a load balancer does. So first of all, here is the icon that represents a load balancer. And what a load balancer does is it is a device that sits in the network and allows us to have a single IP address called a VIP, or a virtual IP address. So here, my virtual IP address is 10.0.0.1, and then that is going to connect to several different servers. So here I have 3 different servers, 10.0.0, 10, 11, and 12. The whole purpose of our load balancer is to have numerous servers that can all respond to requests from clients simultaneously. What this does is it distributes the load across numerous devices. So if we have a very popular website, we can put that website on 3 or more different web servers and then use a load balancer so that when the client connects to it, the client is actually going to connect to IP address 10.0.0.1. So when we have our DNS entry is going to have the website that we're going to, and it's going to map to 10.0.0.1 here. Then when that traffic from my workstation gets to the load balancer, it will direct the traffic to the server that has the lowest load, or whatever policy we implement on that load balancer to make a decision of which server to send it to. A lot of times this will be done round robin, meaning we'll send the first request to the first server, the second one to the second, the third one to the third, and then the fourth one back to the first, and so on. Another way we might do this is the load balancer may send out a health check asking each server how many resources are available, and the load balancer will then send it to the server with the most resources available. If we have multiple devices here, the multiple devices, we're going to send additional traffic to other servers here. So the whole purpose of the load balancer is to distribute load over multiple servers. Now, when we're working in the cloud, this happens in the cloud all the time. Amazon Web Services or Google or Microsoft Azure all have these load balancer services available. It allows them to spin up additional servers to handle additional network traffic from their customers. So load balancers are a critical component in modern networks. Next, let's talk about firewalls. Now, firewalls are a security device. Traditional firewalls operate at the transport layer. So here's an icon for a firewall. It looks like a fast forward symbol for video players or audio players. So the idea of the firewall is that we want to keep our traffic inside our network. We want to keep that safe and secure, and we don't want the internet traffic getting in. The internet is kind of like a wild, wild west of traffic, and almost anything can pass on the internet as just IP packets. So we don't want anybody to be able to get access to our network. So we set up a firewall, and part of the purpose of the firewall is it lets traffic from the inside of the network out, but it doesn't let outside traffic back in unless somebody from the inside sent it. We do this with a series of features with access control lists, where we're limiting IP addresses or a range of IP addresses and port numbers or a range of port numbers. Sometimes we want people from the internet to get into our network. And when we do that, we set up a special area in the network called a DMZ, effectively named after the military version of this, the demilitarized zone. The DMZ, what it does is it allows us to have servers and other services on devices in the DMZ, and it allows us to create a special access control list or a filter that allows certain traffic from the internet to come into our inside network, access the services needed in the DMZ, and then return back to the internet. So this is the whole purpose of our firewall here, is to really act as a secure boundary between our inside networks, our internet networks, and our DMZ or secured networks. Now, not all firewalls operate at the transport layer. Modern firewalls, or next generation firewalls here, actually operate at the application layer. And they're going to do more than just operate at the application layer. They're also going to operate at the transport and network layers too. It's going to have the same type of services available as a traditional firewall, where we can filter traffic based on IPs and port numbers. However, in addition to that, it's going to include something called intrusion detection or intrusion prevention. So these are an IDS and IPS device as well, intrusion detection system or intrusion prevention system. And what's happening here is our next generation firewall has a database built into it. And the database that's built into it has a bunch of signatures of malicious traffic, or of traffic that's undesirable in our network. So what the IDS IPS system is doing is it's watching. So every single message that passes through our firewall is inspected against this database to see if it matches a signature of not desirable traffic. If it matches that signature, what we can do is we can either just automatically throw that message away, that would be intrusion prevention, or we can send an alert to an administrator saying, hey, there's some nefarious activity happening on our firewall. We should go investigate it. Here's the device that's sending it. And this can happen in both directions. So if our computer on the inside of our network gets a virus and it starts sending out traffic that's not standard, we can recognize that and take action. Another thing that the next generation firewall might do is have something called a proxy server or a content filter. A proxy server allows us to filter web and other internet traffic so that our users can only access information that's valuable. At least that's valuable to the business. So we can program that proxy server to allow certain content and block other content. In companies I've worked for, they have blocked Facebook, so they don't want their employees looking at Facebook during the day. Other organizations I've worked for have blocked Craigslist and other things like that, so people can't shop during the day. So eBay and Craigslist are blocked. So a lot of times managers like to use the proxy server to manage their staff instead of actually having to go talk to and encourage their employees to do quality work. We use the proxy server to actually block traffic. Now, sometimes the proxy server is extra important in that maybe we're trying to protect intellectual property, design ideas, and maybe a new release of a product that we don't want to get leaked out into the world. That proxy server can help us filter the places where those events might happen and actually prevent some of that. Another option we have on our firewalls is something called a VPN concentrator. So a VPN concentrator, or another word for this is a VPN head end, is it allows external users to gain access to services on the inside of the network when they're not at work. Now, VPN concentrators and VPN head ends became a critical piece of infrastructure during the pandemic. And what they allowed is it allowed people to work from home and access networked resources in their offices from their home computers. The idea here is that the users have an internet connection at home and they can build a connection using a VPN from their workstation to this VPN concentrator and allow them access to internal resources. A VPN is a virtual private network, and what it does is it creates a type of tunnel through the internet, and that tunnel is really nothing more than putting IP packets inside of other IP packets and then moving it across the internet. And while those packets are inside packets are also encrypted so nobody can see what's happening. So this allows us to give users access to very specific resources inside of our network without compromising security. Another type of firewall that we can have here is a unified threat management device. And this is basically a next generation firewall. It's going to be a layer 7 firewall or application layer firewall. These firewalls can pay attention to specific applications. So instead of just looking at a port number like a traditional firewall, layer 7 or application layer firewalls, next generation firewalls, all of them can actually look and see, oh, this is HTTP traffic. Let's make sure that the person trying to access HTTP is actually doing it from a web browser that's valid versus trying to form some type of attack into our network and tricking the firewall into thinking it's going to a website, but really it's launching an attack. This UTM device also can do content filtering and proxy server, can also do IDS, IPS. So this layer 7 unified threat management firewall, these devices are very useful in helping prevent malicious traffic from getting onto your network, as well as detecting malicious traffic and other types of network attacks that are happening inside your network. You can take action a lot faster. Voice over IP. There's a time 20 years ago when voice over IP was a fad or appeared to be a fad, and now it is pretty much standard across the board of how we make voice phone calls inside of a business. So voice over IP is where we have a phone, and the phone has a switch in it that we connect to the network. I've talked about this before when we had a voice VLAN and a data VLAN, and we actually plug our PC right into our phone. Here I just have our phone shown, it's connected to the network. We give the traffic on that phone priority on our network using some type of quality of service. And then that phone is going to connect to something called a VoIP gateway. The VoIP gateway is going to be the device that handles all the incoming and outgoing phone calls. It's going to be the device that makes your phone ring. It's going to be the device that when you dial a phone number, you're sending a message to the VoIP gateway, and then it's going to use something called a SIP trunk to connect to the plain old telephone service or our telephone service provider. It's going to allow multiple phone calls to happen simultaneously over that data network connection, that SIP trunk. So our VoIP gateway is going to be responsible for actually dialing the phone over that SIP trunk so we can get somebody's phone at some other location to ring. So in voice over IP, we have our VoIP phone. We're going to use quality of service, and it's all going to connect to this VoIP gateway. Let's look at some other devices for enterprise networks that you might encounter. Some of these are pretty common sense, like printers, right? Inside of your network, you're going to have a printer connected to the data network. Now, I've labeled this as smart devices here. We have more to talk about. Printers may not necessarily be a smart device, but it's going to fall in this category of other networked devices. So printers are an important one here. HVAC, this is one you may not think about as being networked, but our thermostats and other controllers for our heating, ventilating, air conditioning equipment is likely to be connected to a network and have some server that's going to control how all the devices operate. So HVAC is a smart device that we're going to see a lot more of in our enterprise businesses nowadays. Another type of device that we're going to see here is physical access controls or card readers. So it's going to be some device that we use. Maybe it's a palm scanner, maybe it's a retina scanner, but it's most likely going to be some type of card that you're issued at your organization that you can use to scan on a keypad or scan on a card reader that will open doors for you, or it may give you access to certain devices. These are all typically networked together in modern systems. So in modern security systems, we're going to use these card readers and they're going to be connected to a data network. Another one we might see here is Internet of Things devices. These might be smart light bulbs, smart speakers, thermostats, refrigerators, doorbells, all kinds of things. A lot of these things we're going to see in our homes. However, Internet of Things devices are becoming more popular in enterprise networks as well. And the reason for this is that they're small and they can collect a lot of data. When I was working for a hospital, that hospital used some smart devices that were in refrigerators, and there was lots of refrigerators in a hospital, mainly to keep medical stuff cold in the right temperature. So there was a company that made these little thermostats that connected to the wireless network and would constantly report back the temperature of the refrigerator. And it could send alert messages then to lab technicians or nurses or other folks in medical areas to say, hey, this refrigerator is too hot or it's too cold. We need to fix it or adjust the temperature on it. Another type of device, of course, is a security camera that's going to be connected to our data network. A lot of new security cameras now are all IP based. They might even connect over the wireless network. So, security cameras are another type of device that we're going to see on our data network that we need to accommodate. And one last one here. This one's a little bit strange. This is industrial controls. Industrial controls and SCADA systems. These SCADA stands for Supervisory Control and Data Acquisition. These are devices that we use in a factory, and a lot of them have been used for quite a long time actually, where manufacturing data can actually be sent to and collected by a central server, and then that information is used to figure out how to make the machines work better or adjust their performance and whatnot. So these industrial controls or SCADA controls, these are very, very, very important in manufacturing. A lot of these require some specialized security because they are more easily attacked because a lot of them are a little bit more antiquated and they weren't ready for modern network use. So these security controls are smart devices in our systems that we use that are going to be connected to the network. They're typically going to require extra special security to prevent them from being attacked. So we have printers, HVAC equipment, security cameras, card readers, IoT things, SCADA devices. These are all types of devices that we're likely to see on our network that require special attention in order to get configured properly. Let's wrap up everything we've talked about here. We talked about load balancers, and we saw how load balancers can distribute traffic to multiple servers to make sure that end users have a quality experience. We took a look at firewalls and took a look at both layer 4 firewalls and layer 7 firewalls, as well as IDS, IPS, proxy servers, and whatnot. We looked at voice over IP, saw how the voice over IP gateway is the central server for making and receiving voice phone calls. And then we looked at other networked devices that we may see in our networks. I hope you enjoyed this course and learned a lot about data network devices and how they operate. Routers and switches are such a critical component of IT, especially data networking, and understanding their operation is very, very important.
You can check in with him later.
So first, let's start with load balancers. Now, a load balancer is. Next, let's talk about firewalls. Now, firewalls are a security device. Traditional firewalls operate at the transport layer.
What's your point of
So
contact?
here's an icon for a firewall. It looks like
Turn
a fast forward symbol for video
from Takeda.
players or audio players. So the idea of the
Does
firewall
he
is that we want to keep our traffic inside our network. We want to keep that safe and secure, but we don't want the internet traffic getting in. The internet is kind of like a wild, wild west of traffic, and almost anything can pass on the internet as just IP packets. So we don't want anybody to be able to get access to our network. So we set up a firewall, and part of the
DPR?
purpose of the firewall is it lets traffic from the inside of the network out, but it doesn't let outside traffic back in unless somebody from the inside sent it. We do this with a series of features with access control lists where we're limiting IP addresses or a range of IP addresses and port numbers or a range of port numbers. Sometimes we want people from the internet to get into our network. And when we do that, we set up a special area in the network called a DMZ, effectively named after the military version of this, the demilitarized zone. The DMZ, what it does is it allows us to have servers and other services on devices in the DMZ, and it
You
allows
see
us to
your
create a
contact person have
special
that.
access
Send
control list or a filter
but make
that
sure you
allows
have that
certain
always.
traffic from the
Yeah.
internet to come
Show that to him
into our
when you
inside
get the
network,
contract.
access the
Okay.
services needed in the DMZ, and then return back to the internet. So this is the whole
See your
purpose
green
of the
card and ID
firewall
pics.
here, is to really act as a secure
Sure.
boundary between our inside networks, our internet networks, and our DMZ or secured networks.
Okay.
Now, not all firewalls operate at the
You can
transport
sign in,
layer.
make it easy for me to
Modern
read. I get
firewalls,
to your
or
badge
next
should be on your way.
generation firewalls here, actually operate at the application layer. And they're going to do more than just operate at the application layer. They're also going to operate at the transport and network layers too. It's going to have the same type of services available as a traditional firewall where we can filter traffic based on IPs and port numbers. However, in addition to that, it's going to include something called intrusion detection or intrusion prevention. So these are an IDS and IPS device as well, intrusion detection system or intrusion prevention system. And what's happening here is our next generation firewall has a database built into it. And the database that's built into it has a bunch of signatures of malicious
Have you been
traffic.
away for
When did you get your card?
some time and just coming back, or
Only like
IDS IPS system is doing is it's watching. So every single message that passes through our firewall is inspected against this database to see if it matches a signature of not desirable traffic. If it matches that signature, what we can do is we can either just automatically throw that message away, that would be intrusion prevention, or we can send an alert to an administrator saying, hey, there's some nefarious activity happening on our firewall. We should go investigate it. Here's the device that's sending it. And this can happen in both directions. So if our computer on the inside of our network gets a virus and it starts sending out traffic that's not standard, we can recognize that and take action. Another thing that the next generation firewall might do is have something called a proxy server or a content filter. A proxy server allows us to filter web and other internet traffic so that our users can only access information that's valuable. At least that's valuable to the business. So we can program that proxy server to allow certain content and block other content. In companies I've worked for, they have blocked Facebook, so they don't want their employees looking at Facebook during the day. Other organizations I've worked for have blocked Craigslist and other things like that, so people can't shop during the day. So eBay and Craigslist are blocked. So a lot of times managers like to use the proxy server to manage their staff instead of actually having to go talk to and encourage their employees to do quality work.
Badge
Use the
number
proxy
32.
server to actually block traffic. Now, sometimes the proxy server is
No,
extra
31.
important in that maybe we're
If you
trying
could
to
sign in, make it easy
protect
for me to read.
intellectual
I'll get you your
property,
badge. You'll be on your way.
design ideas, and maybe a new release of a product that we don't want to get leaked out into the world. That proxy server can help us filter the places where those events might happen and actually prevent some of that. Another option we have on our firewalls is something called a VPN concentrator. So a VPN concentrator, or another word for this is a VPN head end, is it allows external users to gain access to services on the inside of the network when they're not at work. Now, VPN concentrators and VPN head ends became a critical piece of infrastructure during the pandemic. And what they allowed is it allowed people to work from home and access networked resources in their offices from their home computers. The idea here is that the users have an internet connection at home, and they can build a connection using a VPN from their workstation to this VPN concentrator and allow them access to internal resources. A VPN is a virtual private network, and what it does is it creates a type of tunnel through the internet, and that tunnel is really nothing more than putting IP packets inside of other IP packets and then moving it across the
You guys
internet.
have
And
green
while
passes
these
already?
packets are inside packets are also
I hope y'all.
encrypted, so nobody can see what's happening.
For
So
parking
this
here,
allows
right?
us to give users access to very
Yeah,
specific
if you know
resources
how to
inside
sign
the
in, you
network
can sign in.
without compromising security.
Are
Another
you with
type of
him?
firewall that we can have here is a unified
How long will you
threat
be staying
management
here?
device. And this is basically a next generation firewall. It's going to be a layer
All
7
day.
firewall or
All right, no
application
problem.
layer
I just want to make
firewall.
sure you need a
These
contractor
firewalls can
badge.
pay attention to specific applications. So instead of just looking at a port number,
You'll be badge number 32.
What is that working for you, sir? What door?
You can sign in, make it easy for me to read. I'll get you a badge. You'll be on your way now.
Traffic. Let's make
Was
sure
that
that
the
the
warehouse?
person trying to access HTTP is actually doing it from a web browser that's valid versus
Good
trying
morning.
to form some type of attack into our network and tricking the firewall into thinking it's going to a website, but really it's launching an attack. This UTM device also can do content filtering and proxy server, can also do IDS, IPS. So this layer 7 unified threat management firewall, these devices are very useful in helping prevent malicious traffic from getting onto your network, as
And
well
check
as
that you have the correct access. And I saved it again. So
Friday.
appreciate it. Your network, you can take action a lot faster.
Yeah.
Walk around like there you go.
Voice over
Oh,
IP. There was a time 20 years ago when voice over IP was a fad, or
Yeah,
appeared to be a fad, and now it is pretty much standard across the board of how we make voice phone calls inside of a business.
You'll be badge
So
37.
voice over IP is where we
You
have
can sign in, make it easy for me to read. I'll get you your badge and you'll be on your way, man.
network. I've talked about this before when we had a voice VLAN and a data VLAN, and we actually
yeah, it's for an escort to let you in.
Here I just have our phone
walk with those
network. We give the traffic on that phone priority on our network using some type of quality of service. And then that phone is going to connect to something called a VoIP gateway. The VoIP gateway is going to be the device that handles all the incoming and outgoing phone calls. It's going to be the device that makes your phone ring. It's going to be the device that when you dial a phone number, you're sending a message to the VoIP gateway, and then it's going to use something called a SIP trunk to connect to the plain old telephone service or our telephone service provider. It's going to allow multiple phone calls to happen simultaneously over that data network connection. It's SIP trunk. So our VoIP gateway is going to be responsible for actually dialing the phone over that SIP trunk so we can get somebody's phone at some other location to ring. So in voice
number 43.
we have our VoIP phone. We're going to use quality of service.
You can sign in, make it easy for me to read. I'll get you your badge. You'll be on your way.
Let's look at some other devices for enterprise networks that you might encounter. Some of these are pretty common sense, like printers. Right inside of your network,
company
you
name,
have a printer
Junior
to the data network. Now I've labeled this as smart devices
You have
here.
a white,
We have more
white or
about
green?
printers may
White.
not necessarily be a smart device, but it's going to fall in the category of other network devices. Printers are an important one here. HVAC. This is one you may not think about as being networked, but our thermostats and other controllers for our heating, ventilating, air conditioning
Right down
is likely to be
if
connected
it's
to
date.
a
Sign
network
up.
and have some server that's
Just
going to
sign
control how all the devices operate. So HVAC is a smart device that we're going to see a lot more of in our enterprise businesses nowadays. Another type of device that we're going to see here is physical access controls or card readers. So it's going to be some device that we use. Maybe it's a palm scanner, maybe it's a retina scanner, but it's most likely going to be some type of card that you're issued at your organization that you can use to scan on a keypad, scan on a card reader that will open doors for you, or it may give you access to certain devices. These are all typically networked together in modern systems. So in modern security systems, we're going to use these card readers and they're going to be connected to a data network. Another one we might see here is Internet of Things devices. These might be smart light bulbs, smart speakers, thermostats, refrigerators, doorbells, all kinds of things. A lot of these things we're going to see in our homes. However, Internet of Things devices are becoming more popular in enterprise networks as well. And the reason for this is that they're small and they can collect a lot of data. When I was working for a hospital, that hospital used some smart devices that were in refrigerators, and there was lots of refrigerators in a hospital, mainly to keep medical stuff cold in the right temperature. So there was a company that made these little thermostats that connected to the wireless network, and would constantly report back the temperature of the refrigerator. And it could send alert messages then to lab technicians or nurses or
Ephraim,
other folks in medical
Pedro's been
areas to
coming
say,
in
hey, this
early.
refrigerator is too
Yeah.
hot or it's
He
too
goes to
cold. We need
B6.
to
You
fix
don't
it or
anymore,
adjust the
right?
temperature on it.
Sometimes I do, sometimes I don't.
Another type of device, of course, is a
It
security
depends
camera,
on if
which can be
Pedro wants
connected
the
to our
laptop
data
or if
network. A
he
lot of new
kind of
security
doesn't want to
cameras
go.
now are all IP based. They might even connect over the wireless network. So
He
security
went
cameras
yesterday,
are another type of device that we're going to see on our data
and
network
then
that we use
Madrano
to
went the day
accommodate.
before.
And one last one here. This one's a little bit strange. This is industrial controls. Industrial controls and SCADA systems. These SCADA stands for Supervisory Control and Data Acquisition. These are devices that we use in a factory, and a lot of them have been used for quite a long time actually, where manufacturing data can actually be sent to and collected by a central server, and then that information is used to figure out how to make the machines work better or adjust their performance and whatnot. So these industrial controls or SCADA controls, these are very, very, very important in manufacturing. A lot of these require some specialized security because they are more easily attacked, because a lot of them are a little bit more
Hello,
antiquated
security.
and they weren't ready for modern network use. So
Okay,
these
thank
security
you.
controls are smart devices in our systems that we use that are going to be connected to the network. They're typically going to require extra special security to prevent them from being attacked. So we have printers, HVAC equipment, security cameras, card readers, IoT things, SCADA devices. These are all types of devices that we're likely to see on our network that require special attention in order to get configured properly. Let's wrap up everything we've talked about here. We talked about load balancers, and we saw how load balancers can distribute traffic to multiple servers to make sure that end users have a quality experience. We took a look at firewalls and took a look at both layer 4 firewalls and layer 7 firewalls, as well as IDS, IPS, proxy servers, and whatnot. We looked at voice over IP, saw how the
Yeah, by
voice
debugging
over
channel.
IP gateway
Yeah, by
connects to a
debugging channel.
central
Yes,
server for
do you need it out or
making
can you just sit in
the
there?
voice
I
phone
see it in there.
calls.
That's fine.
And we
Thank you.
looked at other networked devices that
It'll be
we're going to
badge
see
number
in our
44.
networks. I hope you enjoyed this course and
If you
learned a
could
little
sign
bit
in, just
about
make it
data
easy for
network
me to
devices
read.
and
I'll
how they
get you your
operate.
badge and you'll be on your way, man.
Routers and
Alrighty,
switches
sounds
is a
good.
critical component of IT,
Ephraim moving between
especially
this
data
white
networking,
parking fence,
and
junior
understanding their
steel,
operation is very,
Vernon.
very important.
What are you waiting for, sir? Badge? Just waiting for his badge.
Yeah.
Okay. All right, thank you.
You have a green card? That's a badge. An ID? Right here. You need badge number 45.
All right.
What's it, right?
Yeah. Thank you.
There you go. Mhm. Why don't we got this? Yep. Yes.
It's up. You
This guy entered without filling out this part. Could you deactivate 44?
44. Yeah. No, still doesn't.
It's a fun. I don't know if you're able to send something out. Yeah, green card. Yeah,
Okay,
green
yeah,
card.
no, open the door.
Yeah, appreciate it.
So when I look at the profile, it says, I got it.
Everybody says that.
Give me just 1 second. I need to call someone.
Yeah, no. One guy was like, "Oh, no, no, no." I'm like, "Nah, you can't." You know, nah,
Thank you. Hello, Lorenzo. Athens is here. Thank you. Be right back.
438. Just point of contact. Your name. This I think I think what's the name on your card? Let me see. Victor. Victor is your contact. Oh, Victor. Yeah, Victor. Whoever signed the green card is your point of contact. Okay. There you go. Thank you. Have a good day. Boys keep coming and coming back to back. More God, more than years. Yeah, you gotta show that card every day. Yeah, no, it's just the only way to get in. Right. You'll sign in after you guys. You badge number 49. All right. Yeah. You can sign in, just make it easy for me to read. I'll get you a badge. You got to be on your list. You already put it? Is that you? Yeah, that's me. You can sign in. What is it, 17? Yeah. 17. Right now, it's about 435. We're at 441. 41. Come on in. And your manager is the person who signed that, so Joseph. That's me. Many contractor settings. DPR or well, yeah, you can pull it up. No problem, man. Next. 55 is going to be your number. You could just make it easy for me to read. Drift on your way, man.
Lorenzo, we're opening the gate. Thank you.
Let's wrap up everything we've talked about here. We talked about load balancers, and we saw how load balancers can distribute traffic to multiple servers to make sure that end users have a quality experience. We took a look at firewalls and took a look at both layer 4 firewalls and layer 7 firewalls, as well as IDS, IPS, proxy servers, and whatnot. We looked at voice over IP and saw how the voice over IP gateway is the central server for making and receiving voice phone calls. And then we looked at other networked devices that we may see in our networks. I hope you enjoyed this course and learned a lot
All right, guys, have a good one.
network devices and how they operate. Routers and switches are such a critical component of IT, especially data networking, and understanding their operation is very, very important.
What is this? Nice. I don't know if you might have to sign in again. All right. Yeah. You're just gonna sign in again. Thank you, man. There you go. Have a good day. Does he have a yes, his green passer?
No.
What company?
Yes, you mentioned. Waiting. Already.
Jacob?
One. One liquidity. That's much good with it.
There you go.
Thank you.
Did he not need it?
Yeah, he just went to the rest of it.
Morning. Do you have your green card on?
Green card?
Yeah, you might want to fill the survey out.
Training card.
Yeah, in order to enter the facility, contractor has to show their training card and their ID to receive a contractor's letter. You can scan the QR code. Once you scan it, it'll pop up like a questionnaire survey. Answer all the questions. Should take about 8 to 10 minutes, and then after you finish, you'll get the email and they'll get you your green card, and that's when you can check out one of these contract cards. If you want, there's like a couch area in there, a common area. You can sit down and, this QR code. You get an error for the survey then. QR code. I'm pretty sure you know how to scan the QR code. Yeah, it's probably he'll help you out. He'll be able to get you. You might have to remove that. What's up, man? Thank you. Give me badge number 72. Yeah, by ID by any chance? Thank you. That was all. If you could sign in, just make it easy for me to read. I'll get you your ID and we'll be on your way, man. Oh. What's your number one? Don't worry about it. It's already written. Just fill out that slot right there. Yeah. Just make it easy for me to read. I'll get you your badge. You'll be on your way. Yeah, I don't think that QR code works. You have to wait. Should we remove that QR code in the meantime?
Let's see if I can.
Yeah. You're welcome. Oh wait, hold on. Let me see that. You didn't fill it out. You have the contractor badge, expiration date, company you're working for, and your point of contact, your supervisor. Yes. So the month that you got it, so it would be October. You could put 2020,
Mr. Taylor
2025
Foltz.
October. Yeah, 10/25.
Sir, your contact person here,
Contact.
foreman. Are you working for DP under DPR?
You're good. You're good.
Justin Rossi, does that sound familiar to you? For contact person?
More. Right, thank you. It'd be badge number 74. Same thing. If you just make it easy for me to read, it's your badge.
You present it to him and he'll give you a contractor badge.
I'm get. Don't forget your badge. Don't forget your badge, man.
Yeah, that's what I didn't get it today.
No. What company was it?
You make.
You make. Thank you.
Thank you.
You need to do morning, man. You'll be badge number 75. Could sign in, make it easy for me to read. I'll get you your badge and you'll be on your way.
My course, Network Concepts.
Who is that? Who is it? Huh? How do you spell is? Do you know Izzy from DPO?
Yeah.
How do you spell that?
IZZY. Let's go with friend.
Yeah, by G. Thank you. You can sign in, make it easy for me to read. I can see your badge, you'll be on your way. I still have to check everyone then.
Oh, I'll help in checking. Once you sign in, then pay you. Okay. That's it.
Sure, you can help him with that. Yeah.
You did send an email like this week, right?
Yeah, they sent it out yesterday. It should be Alberto Leal.
There you go. So what's the future order? You went sequential or you was triple?
Yeah, you can.
Not yet.
Yeah, don't matter.
All right. You'll be badge number 93. You can sign in, make it easy for me to read. I get you a badge, you'll be on your way, man. Anyone else that needs to check in? That should be around there. I'll give you guys a pen. Who's the next person that needs to check in? Get your ID and contact. You'll be badge number 94.
Yeah, 600. That's number.
Yeah, put phone up. You can sign in, make it easy for me to read. I'll get you a badge, you'll be on your way, man. All right, 456. think you took your badge. Sir, your badge? Where you go? Door. Yeah. Oh.
Really?
Number 11. You'll be badge number 97. It's open.
Opening the door.
Great. You'll be badge number 100.
You need hot works today. 3.
You can sign and make it easy for me to read.
Bottom drawer.
Morning.
We can be late. Gotta be gone. So you need an overeat.
Yeah.
Morning.
Against everything.
Here we go.
Dirty. Hello. Oh, yeah.
Get. See, we need hot works. Hot works.
No.
Morning. Oh, yeah, you got a bit every day now. They changed my schedule, dude. They go back. Further? I think it's good. I got out of here an hour earlier. So. You want the other one? So what? You want the other one? Yeah.
75. You open in B6.
I gotta check the cameras. I don't know if it's me or Ruby. Oh, yeah. Early? Yep. Something wrong. No. Oh, she's gonna be here, but not us. Compost.